So everybody, welcome very much to this workshop and tutorial IoT stream for data-driven predictive maintenance. We will start with the tutorial part. So the first 3 hours today will be the tutorial where we will basically have 3 speakers. My name is Slawomir Nowaczyk. I'm from Halmstad University, and I will give a brief introduction and then talk about representation learning. After me, Olga, Fink from Zürich, will talk about domain adaptation. And then we have also Jessica from Volvo trucks, who will give us a little bit of a case study and industrial perspective on how predictive maintenance is important for automotive industry. And then we will have a lunch break, after which we will continue with the workshop. We have a lot of really interesting papers that are going to be presented after lunch. So let me then start by talking a little bit about why data-driven predictive maintenance is so important. And I'm not going into too much detail because since you are here, you obviously understand why this is so important. But I just wanted to give a little bit of an introduction into what predictive maintenance is and what you can actually do with it in the context of machine learning. So basically, predictive maintenance is anything that allows you to figure out the condition of equipment and estimate when to do maintenance. So that doesn't sound very difficult, but it actually turns out to be quite interesting. And the most obvious way of looking at it is if you are trying to do maintenance, there are 2 basic approaches. So one is what is called corrective maintenance, and that's basically when you wait for your equipment to break, and after it breaks, you fix it. And the other one is preventive maintenance, when you are trying to do something to prevent breaking. And if you think about the kind of interaction of the 2, you will end up with this kind of a curve that basically, if you do a lot of preventive maintenance, the cost of corrective maintenance will go down because your equipment will never really break, but it can be really, really expensive. And if you don't do any preventive maintenance, then your corrective maintenance cost will be high because your equipment will be breaking all the time. So there is some kind of an optimal zone in the middle, which decides the right balance between the 2 kinds of maintenance. And that, of course, depends a lot on the details of what kind of equipment it is, how easy it is to predict failures, and so on. But then you can also look at it in terms of how does things change depending on your asset condition. So when you deploy or build new equipment, generally it's in a pretty good state. But of course, there are things that vary depending on the installation and so on. So not every equipment starts in exactly the same condition. And then as it gets worse and worse, there are different approaches you can do, that there is different methods you can use to actually analyze how far it is from perfect condition and how close it is to what you would call catastrophic failure. So you can think of this life cycle and try to imagine that there is a lot of potential for machine learning in different parts here. And then if you look at what I would call success stories of predictive maintenance, surprisingly, there are kind of 2 extremes of a spectrum. On one hand, you have things like nuclear reactors or aircraft and so on. And on the other, very different, you basically have stuff like wheel bearings. And it's kind of interesting, but if you think about it, it makes sense. You have this critical and really expensive equipment where you actually get a lot of really high quality data just because of how critical it is. There is almost no limit to how much data you can get from equipment like this. If you imagine a modern aircraft generates 20 terabytes of data per flight. It's huge amounts of data. You have a really good idea about everything that happens inside. And on the other extreme, you have this really simple equipment where you can do a lot of physics-based analysis. You know exactly what goes wrong in systems like this. So you have very good models that describe what kind of problems you can have, how they will manifest, and so on. So even with really simple sensors, you can do very precise analysis. Now, what I'm personally interested in is basically some kind of complexity spectrum along those two extremes. And for example, I'm working a lot with automotive industry, and Jessica will tell us a lot more later on about the actual practical challenges. But if you imagine a track like this one, it's not quite as complicated as a nuclear reactor, and it definitely doesn't generate as much data as an aircraft, or at least we don't have access to this data. It is just not economically viable to have so many sensors and send so much data. But it's a lot more complicated than a wheel bearing. So it's somewhere in the middle, and turns out it's really interesting and really difficult to solve those problems in the middle. Of course, the automotive industry is not the only it's not the only industry in which we have those kinds of issues. You can imagine this in the energy systems, in the healthcare systems, in smart cities. All of those are somewhere along this spectrum where you have limited information, but systems which are inherently quite complex. So one way of looking at it is what makes predictive maintenance so interesting and so challenging. There are two main things to address. So one is you want to be making predictions from low quality data. In general, in most cases, the data you are collecting is not really designed with explicit purpose of doing predictive maintenance. And the reason is always the economical part. Right? You really want to have this. In the end, you end up somewhere closer to here. So it turns out that you have low measurement accuracy, low frequency of data. The sensors you have are only somewhat related to the properties you really want to measure, and so on. And if you imagine a bus or something like this, that there is a lot of sensors inside, let's say, an engine, but they are mainly designed for doing control, for controlling the engine, not for doing diagnostics. So a lot of the challenges come from the fact that you really want to use this data for something in addition to its original purpose. And then the other big challenge is that the context in which your equipment operates is usually at least partially unknown. So there is a lot of different external conditions that strongly affect what happens with your equipment, but it often gets mixed with the fault symptoms. So when you see something strange in your data, it's hard to know if it comes because the system is getting close to failure, or if it's just being used in an atypical way. So a way of thinking about what kind of data you are collecting, what you can do with it, is to think about, you are getting a lot of those weak indicators from different sensors you are looking at. And interestingly, you can actually divide it into two types of information. So what I will call early symptoms and usage patterns. So early symptoms is an example of certain patterns of degradation that you start seeing. And here you have an example of the blue plot shows the distribution of compressor duty cycle for vehicles with air system faults, and the red one, sorry, without air system faults, and the red one with compressor failures. So you can see that in vehicles with compressor failures, the compressor duty cycle is slightly higher. And basically, what you can also see is that if you compare the faulty vehicles long before failure, more than half a year before failure, with close to failure, less than 6 months before failure, there is also a difference. So we are basically seeing is that this compressor duty cycle changes as you get closer to breakdown date. And that makes sense. Basically, it tells you that as the compressor gets weaker, it needs to work more to provide all of the necessary air. So as you get closer to the breakdown, it works more and more, and at some point it just cannot keep up, and there is a failure. So if you can detect this shift early enough, you now have those symptoms or early signs of the degradation. But there is another type of pattern that is also interesting for predictive maintenance. So if we look at the same population of vehicles, we still look at compressor failures. And now we are looking at a different signal, engine idle time. And we see that that signal also differs between vehicles with failure and those without failure. But now when we look at this time aspect, we see that there is no difference as you get closer to the failure. So it's not the symptom, it's not the fact that the engine works differently as you get closer to failure. Here you see what they call the usage pattern, which basically means that depending on how you use your vehicle, you are more or less likely to have a compressor failure. In this particular case, you can imagine that there is a class of vehicles which drive long distances basically without stopping. They get on a highway, drive for 8 hours, and then stop. And there is a class of vehicles which operate in a city, so they stop at every traffic light and so on. The latter ones, the city vehicles, they will of course use a lot more air. They will use air for braking, they will use air for gear changes. That means the compressor works much harder in those vehicles. So they are much more likely to have compressor failures. But you cannot really use this to decide when the compressor failure will happen. So looking and actually understanding what kind of indicators you can get is really interesting, and how to incorporate this knowledge into machine learning algorithms is really challenging. So from the perspective of this conference and the research in machine learning, predictive maintenance is a really, really interesting application, because you have this wide spectrum of diverse problems where you can vary the difficulty. You basically can say, how much data do we need to be able to do good enough prognostics? So you can have a really difficult problem where your data is really poor quality. And you can imagine that, okay, if we would add more sensors, the problem would become easier, and so on. So it's a really nice test bed for machine learning. And also, you can imagine that there is a lot of different settings in which you can try to apply machine learning, which means you can study a lot of different subtypes of machine learning. So you can phrase predictive maintenance as supervised or unsupervised learning, or anything in between. You can do inductive, deductive, or transductive inference. Active learning, transfer learning, online, federated, all of those kinds of concepts can be applied in the predictive maintenance as an example. And I think that makes it really, really interesting, because you actually can study a lot of different types of machine learning and still learn similar or related things. So this is mostly what I'm trying to kind of cover in this tutorial, to highlight how nice of a test bed predictive maintenance is. So if we look at the main problem characteristics of predictive maintenance, generally it's reasonably easy to collect large amounts of normal operation data. It's not going to always be fully representative, in the sense that sometimes this data can come from lab experiments, sometimes it will come from a subset of customers, usually the ones that the OEM has the best contacts with or whatever. So it will not cover the whole range of all the possible types of data, or all the possible usages and so on. But you can get large amounts of operation data. The really tricky part is getting enough of the faulty data. Right? In most cases, the faults are pretty rare. They don't happen as often as we, the machine learning scientists, would like them to. So they take time to develop. The most common question we are often getting is, if we design a new truck model or something, can we have the predictive maintenance for it immediately? And in many cases, the answer is no. We need some examples of faults, and those faults will appear after 3, 5, maybe 10 years. There is limited amount of things we can do until we have some examples of this faulty data. So there is different ways we can work around it, of course, but that is part of what makes it interesting. In general, you don't know all the possible faults. You don't know all the things, all the different ways in which the equipment can break. So there is always going to be some new surprises. And in many domains, you cannot really do run to failure experiments. So you cannot leave the equipment to actually fail. Sometimes you need to replace it before it fails, and it's difficult to know, okay, so how much remaining useful life was there really? And in many cases, diagnostics is difficult. So you will get equipment, or you will send a technician to an equipment. The technician will replace a couple of different components, but they might not even know which of those was actually broken and was responsible for the failure. So there is a lot of really interesting challenges there. And then you can also think of this as going beyond just making predictions. You can think of predictive maintenance as trying to be some kind of knowledge creation idea, where the real goal is to provide new understanding about the equipment. You want to know what are the actual degradation patterns, what are the use patterns, what are the external conditions that affect this equipment. So making predictions about failures is just the first step, but then you kind of want to help people design this equipment in a better way in the future. And that's, of course, really, really interesting. Touches to a lot of things related to explainable AI or the interactions with experts and so on. So that was the short introduction into predictive maintenance. If you have any questions about that part, or at any point, if you have any questions, you are more than welcome to ask. I suggest you ask on the app. There is a Q&A tab for this setting. So for this session. So if you want. And if there are no questions about that, then I will move to the next part, which is basically representation learning for predictive maintenance. So let's start with the question: why representation learning? What's about them, and why would it be interesting? Of course, in practice, the key to getting success in machine learning is of course feature engineering. You need to make sure that your data is represented in the right way. And as machine learning scientists, we of course would like to automate this step as well. Right? It's by far the most time-consuming step in solving machine learning problems. So why not automate it? And in the areas of image processing, right? Computer vision, deep learning, all of those big improvements in the last years basically come from the ability to learn better representations. And it all, or a lot of this, boils down to being able to take advantage of various kinds of available information. So either in terms of unlabeled data or in terms of transfer learning, we can find those features which are good for solving a lot of different image processing tasks and so on. And then the question is, can we do the same or similar things in other areas like predictive maintenance for other types of data and so on. And then, of course, the question becomes, what does it mean for a representation to be good? What kind of properties do we want in order to have, in order to really be able to say that we now have good representation, have been able to learn it and so on. And there is a lot of research on this in various areas, and there are those properties. You want it to be smooth, you want it to lie on a manifold, you want it to explain multiple factors. There is a lot of really interesting research on these entangled representations, which basically allow you to combine different aspects and create those kinds of fancy images and so on. So there is a lot of really interesting ideas, but the general theory of representation learning is still lacking. We still don't quite understand all the details and so on. And maybe there is an inherent limitation set by the no-free-lunch theorem. Maybe there is no way we can actually have the perfect way of learning representations, but hopefully we can at least get something similar to what is possible to do in image processing in the area of predictive maintenance. And as I said, it's difficult to have those global properties of good representations. But what you can always do is you can try to find some auxiliary tasks that will help you identify good representations. So if your ultimate goal is, let's say, predicting failures, and your limiting factor is the amount of labeled data, you can try to build good representations by solving other tasks. And hopefully those representations will then translate into easier classification problems that are really interested in. There is a lot of techniques going in this direction. You can do this using autoencoders. There is a lot of work on multitask learning, semi-supervised learning. You can use clustering or grouping to find good representations, the denoising autoencoders, and so on. So there is a lot of different techniques. And in this tutorial, I will not be able to go through all of them, of course, but I will try to cover at least a couple of what I think are interesting directions to investigate. And again, due to the time, I will not really be able to go very deeply into the solutions. I'm more looking at this as a kind of inspiration to give you ideas about possible interesting research directions for your own research. So if we look at what is the main challenge with representation learning, is basically we want to find representations that express general priors about the world, right? So we don't want them to be task specific. We want representations or properties of representations which are generally useful. And that's of course difficult to formalize. We can make intuitively explain what that means. Intuitively we get it, but if we try to formalize, make a definition, if we try to optimize for it, we try to build a neural network which has the best possible representation, or if we want to prove that a particular representation is generally good, all of those tasks are difficult. So let me give a couple of concrete examples of research in this area, what is possible, what are the interesting challenges, and so on. So if we start with what we call activity recognition, so basically different ways in which we can understand the usage of equipment. So here we are looking at a forklift, and this is how it operates in a warehouse. It's reasonably easy to collect a lot of data from the internal measurements on this forklift. So we would get data like this, where we have the current speed, the engine, how it operates, and parameters of that kind. And then what we can do is we can record, let's say, a little bit of couple of hours of a video like this, and we can hand label it by saying, here are the activities that this forklift does. So right now it's picking up load, and right now it's driving with this load somewhere else, and so on. So what we would like to have is this kind of low dimensional representation, because if we just have a couple of hours of labeled data and we have a lot of signals, it's really difficult to learn anything from this kind of raw representation. So we would like to have a representation which compresses the raw signals into something hopefully 2 or 3D so that we can visualize it, we can show it to experts, they can understand what this particular machine is doing, and so on. And then one of the challenges we encounter is that, of course, you can do, for example, autoencoders, right? And it's also not terribly surprising, but if you compare, you can make a lot of different types of autoencoders with different architectures. They will lead to different reconstruction errors. And then you can compare those representations in terms of the accuracy, right? Either balanced accuracy or average area under PRC curve, different ways of measuring how good those representations are for the exact task that you are solving, the classification task. And surprisingly enough, it turns out that there is basically no correlation between the reconstruction error and the accuracy you are getting. You would want to imagine that if you can train a better autoencoder, it will lead to better classification. But it's not quite that simple. Right? A good autoencoder which is very precise in reconstructing the signal, will capture a lot of uninteresting parameters as well. And the autoencoder which is worse at doing that, which actually discards some of the noise in the data, might be significantly better for doing the classification. And that also holds when you start looking at data from a different warehouse. So if we now start getting data from similar equipment but operating in different conditions, you can see that the difference in the reconstruction between those two sites can be quite significant. And it also translates into classification performance. So it is really interesting to see what kind of representation can you build in an unsupervised fashion using all of the data you get from the you get automatically from the vehicles. How can you translate it into good representations for whatever classification task you are actually interested in? And in this particular case, we were also only looking for the activities that were expert defined. So we knew that we are interested in, let's say, those 5 activities. So this is what the people from the company expect. But how do we know if those actually are the best activities? Maybe there are other kinds of other ways in which we can describe what the vehicles are doing that would actually be better for predictive maintenance or for any other tasks that we are interested in. So maybe what we want to try to do is to try to find some kind of global states which describe how the equipment operates. So one way of doing something like this is to try to find some kind of Markovian representation. So if you imagine that we are collecting the sequential data from the vehicles, and they represent some kind of partially observable state. So we have our time dimension and we have machines. Imagine that we have multiple similar machines. They all create time series data. Now, what would be potentially interesting to do is we could model this vehicle as a Markov process and try to capture different events in this machine's history. So we basically want to say that there are certain either types of behavior or things that happened to this machine that are common for the whole fleet. And we would like to capture if and when those particular machines have encountered those events. And so basically what we try to do is we try to turn the raw values of the signals we get into some kind of meaningful states, or states to which we can assign this kind of meaning. And then we can have each vehicle described by this trajectory of state, and we can capture both the unusual transitions between states. So we can say that particular state follow another state in a way which is atypical, or we can capture the states which are by themselves indications of, for example, failures. So if you think about how this could be done, if we start from this very simple description of machines and time, the easiest way of kind of trying to find those global states would be to just do clustering. So we collect all of the data from all of the machines, we forget about the time aspect for now, and we just do some kind of clustering. And that gives us first approximation of those states. So now we say that there is this type of behaviors that many machines demonstrate over their lifetime. And then we can go back to individual machine and put those states again on a time axis. So now we have this trajectory of states for a given machine of interest over time. And now if we know that there has been a failure or repair at this particular time, we actually can make a more meaningful analysis, because maybe we can see this particular state doesn't seem to be problematic because the same state happened before and everything was fine. The values might be slightly different, but it's still example of the same state. So maybe we actually should say that this state is more likely to be cause for this failure because it's kind of more unique. And then we can look at in other machines, can we find those kinds of patterns as well? So it's all about getting, not focusing so much on details in the data, but trying to find some kind of interesting aggregations of it. And that was, of course, a very simplistic way of looking at it, because we assumed a fully observable Markov model. In reality, what we have is much closer to hidden Markov model, because there is some kind of actual health status of the equipment that is generally not observable, right? So we observe certain measurements, but underlying it is the actual hidden health status of the machine. And it's this actual health status that we would really like to capture. So we would like to build some kind of hidden Markov model that tries to identify those possible states and so on. That was one approach where it's possible to kind of look at different aggregations of data, but it's also important to look at the context that underlies this data. So if we here switch a little bit from supervised machine learning to anomaly detection, and so if we say we don't necessarily have the labels for all the failures, but we would like to detect anomalies, we would like to detect strange data. Now, contextual anomaly detection is about when we try to identify the object which is surprised, which has this unusual behavior within some kind of behavioral attributes, but according to a specific context. So there is also this concept of contextual attributes. And the most obvious example is something like this, when you have time and you say a particular value might be perfectly fine in the winter, but it would be an anomaly in the summer. Right? So you basically say the time defines the context, and whatever is considered unusual depends on this particular context. And here, of course, the tricky or the interesting part is finding this context. In some cases, you might be able to determine the context from some kind of expert knowledge, but it's also interesting to see, can we do it either fully or semi-automatically, and can we also find some aggregation or ensembles of context, because it's not necessarily that there is always a single context. In many cases, there are multiple potentially interesting contexts, and you want to find the right balance that will lead to finding the best anomalies. So here we are looking at what could be called wisdom of the context, where we are basically trying to combine active learning and ensembles. So we start by identifying a large number of potential contexts. It could be all the possibilities, but that grows exponentially. So you generally want to limit it somehow. And then we have base anomaly detectors, so the typical anomaly detectors that will detect anomalies given each of those possible contexts. And then, of course, the question is, which of those is best? Because different contexts will give you different anomalies. We need some way of identifying which ones are most relevant. And just as with most unsupervised machine learning, the anomaly detection is very much subjective. So it very much depends on what the particular user is interested in. So instead of trying to guess this, we are setting it in the active learning context. So we are looking at asking the expert about examples of anomalies, and from their answer, figuring out what type of contexts they are actually interested in. And on top of that, we have this idea of building an ensemble, because with an ensemble of contexts, we can actually detect anomalies better than with any single one. So we have those examples or the results where we basically can show that if you want something like this to work, you need to find the right query strategy. And if you look at the typical query strategies from active learning, they will not really work very well because of how imbalanced the anomaly detection data is. Typical query strategies will basically not ask about enough anomalies. They will mainly end up asking about normal data. And of course, from that, you cannot really learn that much. So you need to define a query strategy which is skewed towards being more likely to actually identify anomalies. And we can show that this active learning helps, that finding the types of anomalies that the user is interested in outperforms doing it in an unsupervised fashion. And we also show that an ensemble is better than any single context. So that with an ensemble of different contexts, we can outperform every single, including the ground truth context. And the actually reason why it works like this is, if you look, so here is for very simple synthetic data, which consists of a couple of Gaussians. If we look at the number of contexts that give you certain performance, so we look at area under PR curve, and we look how many contexts will give you certain performance. For this kind of artificial data, this is reasonably normally distributed. So then you actually can exploit the diversity in those contexts in order for an ensemble to outperform any single context. And this difference becomes even bigger as you go to real data sets, because in real data sets, the contexts are usually even more skewed. So in many cases, there is a lot of really bad contexts which will not help and actually help performance. And there is very small number of really good contexts. So identifying those contexts is really difficult. So here is where you get the benefits from the ensemble. And sticking a little bit to the idea of ensembles, in general, that there is a lot to be gained by building this kind of diversity and doing ensembles based on that. Of course, they allow you to do variance bias trade-off better, leading to improved accuracy. They also, for example, allow you higher resiliency to adversarial attacks. With ensembles, it's harder to find adversarial examples which fool all the members of the ensemble. But of course, the challenge or the main trick to building ensembles is the diversity. You need to make sure that those ensembles are making different decisions. And here is kind of a typical picture of the decision boundaries you would get if you try to use methods like bagging or boosting, where you build this diversity through subsampling of the data and similar approaches. And what we actually are showing is that you can make much more diverse classifiers if you focus more on this representation diversity. So here are some examples of how diverse decision boundaries you can make if you actually play with the underlying representation of the data. And of course, you know that in building ensembles that the most important part is this diversity. The performance of individual classifiers is secondary. You really want to make sure that you get the diversity right. And if you think about how this can work, the most typical way you would do it here with the example of neural networks is you want to have this kind of parallel part where you try to build different representations through number of layers in the network and so on. And then you want to have the serial part, which kind of combines all of those representations into the final classification output. And the tricky part, of course, here is how do you ensure that those representations that are learned are diverse. And one way that you actually can do it is you can, in this parallel layer, build some kind of, or add some kind of orthogonalization layer where, for example, pairwise, you ensure that there is not too much mutual information in between those representations. And if you have good representation learning techniques, you actually can do this because there will be multiple representations which are all good, even though they remain diverse. And so if you guarantee that those representations will be diverse, you can end up with a pretty good classifier at the end. And here is an example of what that actually means in practice on NMIST dataset. If you look at, so here are 4 different models trained on digit 0 with orthogonalization, and here are 4 without. So if you look at those without orthogonalization, they are not exactly the same. Of course, they are training on different subsets of data and so on. So there is some diversity, but the diversity is not that big because they are all kind of trying to do the same thing. They are all trying to capture all of the digit 0, while the representations with orthogonalization, they specialize significantly more. So each of those identifies a particular feature or particular aspect of the digit 0 and focuses on that, while others focus on something else. Right? And it's the same thing for different digits. You can see the same pattern. Each of those representations is kind of, without orthogonalization, is trying to be more or less complete in capturing the digit, while the orthogonalization guarantees some kind of competition and thus diversity of the representations that the system is learning. So then the final thing I wanted to talk about today, I want to leave at least 5 minutes for questions, is about hierarchies. And now I'm actually going to switch a little bit, because what I was talking until now was representations of the data. But you actually can find different representations or different structures, often also in your labels. Because if you imagine a complex equipment like a truck, there is a lot of different faults that can happen, right? Many different things can go wrong. And the really interesting part is that those failures are related. They happen to different components, but those components are all building the whole truck. So the typical way of handling it is to build one classifier per fault. But that means that you are losing a lot of information, and you are also becoming much more dependent on the accuracy of the diagnostics data. if it turns out that the, for example, decaying information is not perfect and the actual cause of the failure was something else that you think, you might end up with really noisy labels. So instead, what you would want to do is you would want to look at the track as a whole and actually model the fact that there is a number of different problems that can happen and they are not really independent. And then you will discover that some faults are really easy to mix. So it's really difficult to distinguish between them, while others are really distinct. Like it's really easy to say if it's fault A or fault B. So then the question becomes, can we actually learn this structure? If we want to help technicians in identifying the faults, can we learn this structure somehow and actually get better results than by asking binary questions one at a time? Is it fault A, yes or no? Is it fault B, yes or no, and so on. Turns out you can, and of course the most obvious way of doing it would be to phrase it as a multi-class problem. So basically saying, okay, I have this data and there is 100 or 1,000 different possible failures. Let's try to learn all of them at once. And in some cases that can work, but there is an inherent difficulty in learning multi-class problems. If you imagine a very simple scenario, and this is of course artificially simplified, but I think it highlights a really interesting point. If you have those two problems and you train classifier A to distinguish green from blue, and you train classifier B to distinguish black from red, it's obviously really easy, right? You can get those kind of results very quickly. Now, however, if you phrase this as a multi-class problem, you want to try to learn one classifier that separates between those four classes. Turns out it's surprisingly not so easy. If you try to, and of course, here I'm purposefully focusing on a decision tree because this kind of a problem is particularly challenging for decision tree. So if we try to learn decision tree of depth 1, the best we can do is this, right? And of course, yeah, we can say depth 1 is clearly too small to solve this problem. We need to have deeper tree. If we go to depth 5, okay, now our green and blue boundary is getting slightly better, but we probably need to go a little bit more. We go to depth 9, okay, it's looking pretty good. We got to go to depth 15. This boundary now is looking fine. This is probably the best we can do. The problem is we are now losing performance on this, the red and black part. And it's on one hand really surprising because this boundary is really easy for a decision tree. However, if we make the decision tree sufficiently deep, it will overfit. So the problem, in a sense, is that there is no parameterization of the algorithm which allows it to solve both of those problems correctly. And of course, you can do pruning, that there are different ways. If you make the algorithm more complicated, it will solve this trivial problem. But it's just here to highlight the big kind of the underlying challenge of, if in case of multi-class classification, you will have very diverse decision boundaries. And one thing we have learned in doing machine learning, of course, is that you really need to adapt your algorithm and the hyperparameters of your algorithm to the problem that you are trying to solve. We were all familiar with the no-free-lunch theorem. There is no algorithm that can solve all the problems all the time. And the more diverse those decision boundaries are, the harder it is to find the algorithm and the hyperparameters that will be able to solve all of them at once. So what you actually would like to do is you would like to separate your problem into simpler, more homogeneous subproblems. And one way of doing that is through building hierarchies. So you actually can, if you have many different, let's say, faults to discover, you can build a hierarchy of those faults. And you can show that with such a hierarchy, you can outperform single classifier. You actually can outperform single classifier in many cases just by doing random hierarchy. So if you split your multi-class problem into problems randomly, into subproblems randomly, you will often outperform a single classifier already. But of course, if you build this hierarchy in a good way by correctly measuring the similarity between classes so that your most similar or the right that is find the most similar classes and build hierarchy based on this similarity, you will end up with even better results. And then the tricky part is how to measure this similarity. And it turns out that you really need to measure the similarity in relation to your algorithm. So you can also show that depending on the algorithm you want to use, the correct structure of the hierarchy will also change. And in general, what you want to get, or what you observe, is that because the multi-class problem is inherently harder than the sum of its parts, if you try to use some kind of non-hierarchical classifier, you will have this extra difficulty which will lose the performance. And the really interesting part is that this difference between hierarchical classifier and non-hierarchical one depends on the quality of the models that you have. Because on the two extremes, it's really easy. Like if your models are really, really good, if you make perfect decisions between all the possible pairs of classes, of course, you don't need hierarchy. There is no room for improvement there anymore, right? You get perfect predictions anyway. At the other extreme, if your models are really, really bad, if they are basically making random guesses all the time, there is also nothing you can gain by doing the hierarchy because there is no structure to exploit. It's in the middle when your models are somewhat good but not perfect that you can find this particular structure that is worth exploring. You can find let's say pairs of faults which are sufficiently similar that you kind of want to bring them together in the hierarchy, and that can lead you, can give you a better performance in the end. Okay, so I'm running out of time for my part, so I will close here. And if you have any questions, you are more than welcome to ask them in the Q&A in the app. So I see one question about receiving the presentation. Yes, we will definitely put the presentations on the tutorial website after today, and we will also make the videos available. Assuming my Zoom crashing didn't break the video, we will make the videos recordings available in the app here. So, any other questions?
Can we ask the questions like this?
Yeah, sure.
So I wrote two questions in the Volvo app. So I might just ask them like this. So first of all, those hierarchies which you built, what do you mean? So let's say I have 4 classes A, B, C, D. So would you just more or less, at least in the random setting, artificially build in hierarchy where you say, well, let's assume I would have also 2 more labels, A, B and C, D. So these are labels. And then I first try to separate the label A, B and B, C and C, D. And then in the second step, I would then separate, classify, if I say, okay, I go into the label A, B, then I would try to classify it whether I have an A or an B. Is that what you mean?
Yes, that's so pretty much it. So here is an example of this kind of hierarchy, right? And it can either be balanced or not necessarily balanced. It can be binary or anything else. So here is a binary one, but not balanced. So basically, at any step, you are making a decision between subsets of your classes. Right? So for example, here we would have the first decision the classifier makes is between class called other and all of those. And then depending on this decision, you will train a different classifier to make separation between different classes.
But I thought that is actually what a decision tree is doing in a way, trying to split the entire search space or the input space into subsections so that the subtrees, if you will, become more pure. So in a way, if you have an artificial hierarchy, you are also making, I mean, AB and CD in itself is more pure than the original node ABCD. So it seems that you are just doing the same thing, or like you're just pre-processing, or maybe that's it, you're processing the whole thing to make it easier for the decision tree. I'm not sure, but it feels like you're just recreating what the decision tree would do automatically. But I mean, obviously I'm wrong, but
well, I mean, there is definitely similarity, right? Okay, the hierarchy, but what you can see here, yes, there is obvious similarity to a decision tree, right? The really important part is, of course, that it's just what is the criterion for making a split in a particular node. And in the case of building hierarchy, each node is basically saying that at this stage, we want to group certain classes. Instead of, if we have classes A, B, C, D, instead of building a classifier for separating into 4 different classes, we say we would like to separate A and B from C and D. So it becomes a binary classifier which just tries to separate between those two. And yes, in a sense, it gives you more pure data set, but you wouldn't be able to capture exactly the same type of pureness with any of the typical decision tree. Maybe you would look at the entropy or Gini index, they wouldn't give you the same splits. Right? So it's just a different optimization criteria in a sense for the splits.
So how do you build that then this hierarchy? Are you using some sort of, I mean, a smarter hierarchy than just randomly putting A and B together? Or would you use some sort of clustering beforehand? That would be the obvious thing that would come to my mind, but maybe there are smarter ways. I don't know.
But basically, yes, this is along those lines. And the most important part is how do you measure the similarity between classes? Right? If you have class
Yeah,
A,
exactly. Exactly.
How do you know how similar they are? And there is a couple of different ways in which you can do it. The simplest one is you take, for example, center of mass for a class, and you just measure Euclidean distance between those centers. It's really fast. It generally works fine, but not great. Right?
Yeah, no.
In reality, what you probably want to do instead is you actually can measure the distance in terms of the classification performance. So you can say, if I want to know how similar A and B are, I can just look at the reverse of the accuracy. If I can separate them very well, then they are not similar. If I am making very big mistake in trying to discriminate between them, that means they are pretty similar.
Okay. Well, maybe some like stuff like optimal transport or something would be also useful as a measurement, like Wasserstein distance or something like that. Mm-hmm. There have been a lot of talks on this conference where I got to know this kind of concepts.
Mm-hmm. Yeah, there is actually quite a bit of research on building hierarchies, and there is a number of different ways in which it can be done. I mean, the thing that really was interesting to us when we were doing this was that even a random hierarchy often helps. Right? And that's not obvious, but that comes from this inherent difficulty of the multi-class problem. So then that makes it even harder to evaluate how good your method for building hierarchy is, because you basically, you cannot just beat the single classifier, you need to beat the random hierarchy as well. And turns out surprisingly many papers who propose methods for building hierarchies would just compare to a single classifier, not to
my
a
second
random one.
My second question is, how do you test your results if you don't have labels in anomaly detection in industry settings? Because if you're using this in applied data science, then a company might give you data, say, please find our anomalies for predictive maintenance. I mean, I have this setting right now, and but I don't have any labels, so how I don't even know how to report to them whether I'm good or not, because nobody knows, even I don't know. So this is a very practical but also theoretical and both basically problem. Maybe you can share some insights.
So I definitely agree, and yes, it is a big problem. I think there are two parts to answer to this question, and one is from scientific perspective, and one is from the company perspective. Because as you can probably guess, we are doing a lot of collaboration with companies as well. And in our experience, companies don't necessarily need the same level of rigorous validation. So if we can convince them that the method we use is good one, and then we tell them, so here are the anomalies that this method has found, they are looking for those anomalies for a reason. And they want to do something about them. They want to repair them, or I don't know, charge people extra for using equipment incorrectly. But whatever the reason is, they have some reason for finding the anomalies. And generally, I found that if we give them those examples, they will act on it, and then they will give us feedback if it was what they were looking for or not. So from the collaboration with companies' perspective, I think if it's not something very unique where you actually don't trust your method, I think it's perfectly fine to give them some examples of what was found, and then they will tell you if this was good or not. They would, of course, prefer to know for sure, but if you tell them that you don't know, they will do something that they will either go to the equipment and check or anything else to actually validate if those anomalies are interesting or not. So from that perspective, I think it's mostly fine. The challenge is, of course, publishing those results, because if you want to publish, then you really need to have some measure of performance. And
yeah, or even just in my own, even in my own development, if I don't have anything to test against in my lab, then I don't know, I cannot check. So I need some sort of measurement to see I developed 3 different approaches. I developed 3 different computer programs, if you will, and which one is better? I don't know without. So what would you do then?
Well, I would report all 3 or anomalies found by all 3 to the company and say, here are some differences. Let's figure out which one works best. And I agree. As long as it's free and you can argue for the differences and so on, it's fine. In this kind of a setting, you cannot do the thing that most people do in supervised learning, which is, okay, let's do a hyperparameter grid search over 10,000 different parameter combinations and see which one gives you the best result, right? That kind of approach doesn't scale. So you really need to make sure that you can justify your methods. And I think it's perfectly fine to have a couple of them, but you cannot have thousands. That's a very, very important point.
So basically, I need to know my math so well that I'm just convinced of the results because of my math is so great. Basically.
Yes, basically.
Okay, can I comment on that maybe, sir? So sorry, because we have been also working a bit on that, and so one of the ways to do it is to test your methods on a benchmark data set, to demonstrate your results on a benchmark data set, and then to show the comparison. But another direction that we have been working on was to generate anomalies synthetically, and then to test your approaches on that synthetically generated anomalies. But for those, it depends on if you have any expert knowledge on how the anomalies actually look like and how they are manifested in the signals. So these are a bit the directions that we are at least pursuing. On the one hand, to fine-tune your hyperparameters, because obviously for anomaly detection it's difficult to fine-tune your hyperparameters, but also to convince the project partners from the industry side.
How did you build these anomalies? With which method?
No, it's it really depends. So there were different approaches that we were following. So on the one hand, we assume that we know how types of anomalies look like, then we try to mimic the anomalies, the real anomalies. It was at least sufficient to put in some jumps in the signals. So these were the anomalies that we observed. But then you need to look into how their anomalies are cross-correlated across the signals. But on the other hand, what we were also looking into, and that's a bit of ongoing research, is to look into the feature space, and then to develop anomalies in the feature space and to test them on the anomalies developed in the feature space. But this is really ongoing research. We haven't had. So we had just a student who was working a bit on that. There were some promising results, but we haven't yet published anything on that as well. But maybe we should give the participants 5 minutes to at least to have a coffee break. I'm sorry that I've jumped in.
No, that's great. And
yes,
I completely agree.
Great.
If your method is sufficiently general, then there is a lot of data sets on which you can try it, right? But if your method is designed for a specific purpose, then sometimes it's hard. So that depends a little bit on what exactly you are working with. And similarly, in many cases, you have some idea for what kind of anomalies you are looking for. So then you can introduce something into your data and see if you actually find it. In many cases, you don't, right? In many cases, the point is, okay, we know that there is something wrong, but we don't know what kind of anomalies we're looking for. That limits it. So there is no free lunch. There is no easy answer to that. But there are some things you can try.
Hi, I have one last question about. I'm from industry. I'm from ASML. My name is Anjan. So about it's really great talk. Nice overview about the representation. The question is about in industry we suffer a lot with the quality of data and imbalanced data sets, which are heavily skewed. The representations which you showed, in such a setting, which representations would you pick to represent the predictive maintenance data?
It's really hard to say which representations. That depends on a lot of different factors. I don't think I can give like an answer of representation A is always going to be better than B or something. I think that the whole point of doing representations is exactly the challenges you are talking about. If your data is of really high quality and you have all the labels you need and so on, you don't need to do it. You can just do be it deep learning or any other model, you make your training, and that's fine. I think that the main reason when you need those kinds of approaches is when you have generally a lot of data which is only somewhat related to the task you are trying to solve, right? So the idea of our representations is you can use other information to build something that will then help you with the real task you want to solve. but how to do it depends a lot on what is the task you try to solve, how closely the data is related, how much of it you have, and so on. But I mean, if your problem is, again, you talked about noisy data, and that can also mean a lot of different things, right? But if you mean things like imprecise measurements and missing data and so on, there has been a lot of research on using various forms of autoencoders for building representations which are robust to exactly that. Right? If you can find some results related to, for example, how to build autoencoder representations such that it is resilient to large amounts of data being missing, because it basically will build a representation which aggregates a lot of different signals, and then if a couple of those are missing, it can reconstruct them automatically and so on. So there are different approaches for handling different kinds of problems, and it's similar in case of, for example, highly imbalanced data. In problems with highly imbalanced data, the challenge is, of course, that you have a lot of data for majority class, which basically becomes useless because your performance is limited by the minority class. And then the question is, can you build a representation based on the majority class, maybe even treating it as an unsupervised setting, so that the problem becomes easier and so on. But I cannot really give you very concrete answers here.
Thanks. One last question about the context and the anomaly detectors for context. If you know the domain very well, or if you know the context, it's easy to set them. Is there a framework to mine context?
So the work we are trying to do right now is exactly that, to identify contexts. And in a sense, I agree with you that in some cases you do know the context. But I think in reality, in many cases, you don't necessarily know all of this context, that there still might be there might be other attributes which would be useful as a context, even though you haven't identified it as such. Right? So I think there is still benefits to trying to identify more, even if you suspect that you know at least part of the context. And I think it would be really interesting, we haven't looked at that, how can you combine those two things? So if you know you have some idea about the context, how can you learn even more about it from the data? Would be interesting.
Thank you.
Okay, so now it's time for Olga's presentation. I have eaten all of your break. Sorry about that.
Hi everyone, welcome from my side, and yes, sorry that you're not having time to have an additional coffee. We still hope that you will not fall asleep during the talk. I'll do my best not to keep you a bit awake. So let's, a lot of the things that I was actually planning to, the achievements that machine learning and artificial intelligence algorithm have shown in the last, in recent times. So just at the beginning of 2020, Google has announced that the algorithm were beating domain experts in detecting breast cancer and mammography images. But also what we've seen is that the baseline in language understanding tests that was set by humans some time ago was constantly being overachieved by several algorithms, and that has even resulted that the data set and the training data set has been actually developed more complex, or that the algorithm have really now something to learn also from, because apparently the ceiling has been achieved what the algorithm could learn. But what most of the algorithms have in common is that on the one hand, they really need a lot of representative data, and this has been achieved for computer vision, for example, with the ImageNet dataset. And typically they also require supervision. So it's not just that they require a lot of data, but they also require a lot of labeled data. So they need to know what is there to learn in the data sets or in the specific patterns. And if you look into the predictive maintenance, what we actually are trying to achieve is to detect, to diagnose, and to predict the faulty system conditions. And for the case of a railway wheel, well, in this case, the defects that we would like to detect and to predict are, for example, flat spots or non-roundness. And this is quite a simple system. So there we really know what we would like to detect, and this is in this case faults are actually our labels, and this is what we would like to learn from normally. However, if you look into the critical systems, and as already Slawomir has covered in his talk, so in these critical systems, faults are typically quite rare, particularly if we are considering safety critical systems, because they could simply not be afforded. And obviously, if you wanted to collect larger data sets, we could just we could either wait, or we could have more diverse or larger fleets of such systems that we could collect data from. And in a lot of cases, it's actually quite individual systems, and then it's not possible to wait so long so that we have sufficient patterns to learn from. And how about new systems? Normally, as also Slawomir already pointed out, well, if we take a new system into operation, if we want to use the data to learn from, we would need to wait for a couple of years at least until we have collected some patterns, but even then we are not sure if we have collected sufficiently. And even so this is true for the faults, but even if you wanted to collect representative operation conditions, due to high diversity of operating conditions, we may not be sure that we have collected sufficiently representative data sets. And the question is, so if we have such a high diversity of operating conditions, do we need then to develop algorithms for each of the operating conditions if they are so diverse? Because if we mix them, the algorithms start to performing not so well. Or do we need to develop it for a specific component? Can we go to the fleet level? So that's a bit of the questions, and it highly depends on the systems. And some part of the solutions or of the answer to this question we can actually find in transfer learning and domain adaptation. So since I'm not sure how familiar you're in general with transfer learning and domain adaptation, I'm not sure if you are experts rather on predictive maintenance or rather on transfer learning or domain adaptation. I'm just covering very shortly the basics, and then I will go to the specific applications and the specificities when we apply it to diagnostics, for example. So if you look at, if I asked you what is actually this, and if I ask you to capture this image, well, these are two persons having a conversation. And if I ask you to label this, well, in this case, it would be actually quite the same, but it looks a bit different. And again, we have still two persons or two objects having some type of a conversation in this image. So what we're actually having is we are transferring the knowledge between the different domains. And for example, we can transfer something from high quality images, in this case, to low quality images. We can transfer something that we learn for daylight, also for the sunset. And if you have collected data for some images that were collected under perfect conditions, we can also start detecting them also in the wild, but also we can transfer from the art to the surveillance videos. And for humans, it's actually quite easy to do it, but the question is, how can we teach machines to do that? I didn't find a newer graph on that. So Andrew Ng was giving a tutorial in 2016. And this was his perspective back in 2016, so I did not find a newer representation of that. But his perspective was that transfer learning will be one of the driving forces for machine learning and deep learning, while supervised learning was actually the driving force, particularly in the first development years. So obviously, transfer learning is quite simple for humans. So if we have someone who plays classic piano for human, it's easy to transfer it also to jazz piano. If someone is very good in math, then the person will be also is able to transfer this knowledge to machine learning as well. And if you ride a motorbike, it's also easier to transfer it to driving a car. And transfer learning is defined as the ability to apply knowledge learned in previous tasks to novel tasks. If you look in the traditional machine learning, so what we typically would have is that we have an isolated single task, and then for each of the data sets, we would develop the separated single algorithm. But if you look into transfer learning, so on the one hand, we have, for example, a bigger data set and we learn something for that. And then we are trying to transfer this to another data set where we have less knowledge from, but are still trying to achieve a good performance on that second data set. And if you look into the context of predictive maintenance, what is there to transfer and what we would like to learn from? Well, as we already have seen in the previous talk as well, we typically don't have sufficient labels. So if we have a data set with sufficient labels, we would obviously like to benefit from there. But also if we have a data set that it has sufficiently sufficient variability of operating conditions, we would also like to use that data set and the models that were developed with it and transfer this collected knowledge to something where we have less experience on. And on the one hand, we would like to transfer between different operating conditions. So for example, if we have not observed yet faults under some specific conditions, for example, under the path load, but we have observed it in base load. So we would like to be also be able to transfer it there. But also if we have large fleets of units, but maybe not even large, it can be even between 2 units. And if we have sufficient data for one unit that has been operated for a while, we would like to transfer it to other units as well. And ultimately, we would operators have typically, for example, buses from different manufacturers, and some of the components are actually quite similar. So they would like to transfer what they learned from some units to the others, and irrespective of the manufacturers. And one of their challenges here is that, for example, not even the condition monitoring data would be exactly the same. But if you look into the fleets of that are manufactured by the same manufacturer, of course, there we have more similarity. But if you look into the different manufacturers, then it becomes more challenging and more diverse. And I'm going to cover actually the first 2. The third is rather research direction and still a challenge. So the basic idea is that we have a well-trained algorithm and we have the source task, and we would like to adapt it or to adapt to the new domain on the target task. And we have some variations of that. So on the one hand, we can have the same task, same domain, but different tasks. But we can also have different domains and same tasks. And for example, for the same domain, if we take the ImageNet data set, we would still apply the ImageNet data set for the classification task, but also for the segmentation task. And the representation would be sufficiently good for that. But for example, for the different domains that we have, images that we train for a car under normal conditions, and we would now like to transfer it to videos that were captured, for example, under rainy conditions, but we will still like to detect the pedestrian. So that is different domain, but same task, and the other case is where we have the same domain, but a different task. And there are different combinations of it, so we can have the same domain and the same task. So this is the traditional machine learning. We can have inductive transfer learning, where we have the same source and target domain, but different and related source and target tasks. For the unsupervised transfer learning, we have different but related source and target domains, and also different but related target tasks, source and target tasks. And lastly, we have the transductive transfer learning, where we have different but related source and target domains, but we have the same task that we would like to apply it to. And this is particularly what we are going to focus on. So this is where domain adaptation comes into play. And in our case, what we are normally considering is unsupervised domain adaptation. So in this case, we do have labels for the source data set, but we don't have any labels for the target data set. So that's the context of the unsupervised domain adaptation. So we are really trying to benefit from the labels that we got on the source domain. And we are going to make it a bit more difficult in the very last presentation, the very last part of the presentation, where we are trying to look into the case where even the source domain does not have any labels. But let's start rather with the simpler cases. And one of the most of the best performing algorithms in domain adaptation has been the adversarial domain training neural networks. And I wanted to take a look with you on that with the fault diagnostics. So what we have normally, if we have a source data set and we have a train classifier, and it worked quite well. So if we take the very same classifier and we apply it on a target data set that is that does not have or that has experienced a domain shift, our classifier will actually perform quite poorly. So this is the case where we took images under ideal conditions, and then we are trying to apply them or to detect the objects under real conditions. But this is also the case for industrial applications, where we collect the data on some operating conditions, we would like to transfer it to other operating conditions. The general setup for the unsupervised domain adaptation is that we have the labeled source domain, we have the unlabeled target domain, so we don't have any labels at all for it during the training time, and we would like to overcome the domain gap and then to align the two distributions so that we have domain in different representation here. I'm sorry. So for the adversarial training, probably most of you are familiar with, and then in the adversarial training, we have on the one hand the generator, and the task of the generator is to generate images that are as real as possible, and the discriminator, the detective, is trying to distinguish between the real data and the generated data. And obviously the goal of the discriminator is to be able to distinguish between the two, and the goal of the generator is to make the samples that are generated as similar as possible to the real data set. And this same principle is applied also in the adversarial domain adaptation. So we have two parts, and on the one hand, we have the domain discriminator part, and the goal of the domain discriminator part is to be able to distinguish if the sample is coming from the source or from the target domain, so to make them distinguishable. And on the other hand, the task of the domain generator, of the feature generator, is to make them, the two domains, as similar as possible, so that they are indistinguishable in the feature space. And the algorithm that was proposed for this type of applications is the gradient reversed layer. And we have normally three parts here, and we have three parts in the loss. So the first part that we have is actually the feature extractor here. So the goal of the feature extractor is to make, on the one hand, the classes distinguishable between each other, but on the other hand, to make the domains as indistinguishable as possible. And on the other hand, we have the classifier loss, and the classifier, or so it goes here in the classification loss here, and the goal is to minimize the misclassified classes. And on the one hand, for the domain classifier, the goal is again to be able to distinguish their domains as well as possible. And we are putting here additionally a lambda weight here, and it goes with the minors. So this is why the domain discriminator actually becomes indifferent between from where the samples are actually coming from and how indistinguishable the domains are becoming. So that's the basic setup, and that's the basic loss, and the trick here is the gradient reversal layer. So it's just a flipped gradient that is applied here. So what we would normally like to apply is to align the relevant operating conditions. And if we have these setups, on the one hand, we have the source data set, and for the source data set, we have all the faults that have been observed. We have a healthy class, and we have several faulty classes. And then we have a target data set, and we would like now to be able to classify the target data set as well without having observed any pattern or any faults on it. But one of the conditions here is that we are assuming that all the different fault types that we observed on the source data set are also present on the target data set. And we performed a case study on it on quite a well-known benchmark data set. That's the case Western Reserve University Baring data set. It does contain 10 classes. It's one healthy class and 9 different faulty classes with different fault types, and then with different severity of the fault types. And there were 4 different loads that were applied to it, and the loads are considered as being different domains. So they are different sequences, and we applied an FFT on it, which was a typical pre-processing step. So for the basic network, we took the same backbone architecture that was already applied on in another case study that was performing quite well. So we took the very same architecture for that network, and the goal is to have a well-classified fault classes on all the different loads. So we have the feature extractor, we have the classifier, and the question is how can we add actually the domain adaptation here? And one of the ways that was applied, that is applied in domain adaptation is to align the distributions and the intermediate layers. And the approach that is known for that is the adaptive batch normalization. The idea here is that we are actually applying layer-wise adaptation by updating the batch statistics. So normally we would apply the normal batch normalization, but now we're actually distinguishing between the source and the target statistics, and then applying it actually layer-wise. So it's quite simple to apply. It's computation not that expensive. But of course, it's not optimized because we are not integrating it in the learning in the loss function. Another way also to apply domain adaptation is to apply the maximum mean discrepancy minimization. The idea here is that we can estimate the distribution difference between the source and the target with the maximum mean discrepancy. And add it to the loss to be minimized. And of course, it is quite well performing since it directly estimates the distance between the source and the target distribution. But on the other hand, it's quite computationally expensive to do it. Yeah, that's the question to apply it or not. And there's already introduced before the third application or the third method that was applied was the domain adversarial training. And as already described here, we did have, we have part of the losses minimizing the classification loss. On the other hand, we are minimizing the discriminator loss with respect to the discriminator weights, and we are maximizing the discriminator loss with respect to the extractor weights. So we are applying the gradient reverse layer on it, and that's the basic setup. So for each of the 3 approaches, there was the same basic architecture, there was the same budget for hyperparameter tuning, the same optimizer, and the same learning rate, and that's the results that we obtained. So that's so the baseline is if we just train it on one domain and we apply it without any adaptation on the other domain. So the mean performance is still quite well. So we have around 95%, which means that it's not such a difficult domain adaptation task. However, if you look, so they are both the MMD and the domain adversarial neural networks are achieving around 99%. And even the RDBN, which is quite simple and computation not that expensive, is still improving the results. If you look into the efficiency, it's so obviously the RDBN is computation less expensive, and the FMD is the one with the highest computational cost. So this was the case where we are able to use all the data, also where we have access during the training to all of the fault and healthy classes. So that's the basic assumption that we were using to perform this classification to apply domain adaptation. And the same is for the target testing data sets. So on the target, we are assuming again all the faults that we have collected on the source, but then also that we used during the training, and then we have a representative data set over all the 3 data sets. However, this is not the case at all when we are looking into fault diagnostics, because we cannot assume that all the faults have already occurred at the point in time when we're trying to design or to develop our models. So this is the whole idea, that we are able to use our models actually early on and are not waiting until we have collected sufficient or all the different fault types. So the question is, can we still do something with it, or is it still useful to start transferring even if we have not observed yet all the different fault types? And in the literature, there were such approaches that were proposed. However, what they assumed is that on the source data set, we still have access to all the possible classes, from the healthy to all the faulty conditions. For the target, it's assumed that it's just some classes that are available, but then the same we have during the target test, that we have the same classes that we use during the target training. So that is helping a bit, but still it's a bit unrealistic because we may experience additional fault classes during the operation. So the setup that is actually more realistic for the industrial conditions is that we can assume that we have a unit that has collected sufficient data where we have all the classes available. However, during the target training, we cannot assume that all the classes are present, but just that some classes may have been observed. But for the testing, we would like to test it on all the different fault types. So we would like the model to be ready to be applied and to have a high performance on all the possible classes and not just on those that we observed until the training time of the model. The naive assumption would be we can still perform the same that we did before. We have the source training data set, we have the target training data set, and then we can start aligning it. Well, the problem is, since the target training data set does not have now the full representation of the source training data set, we will end up with the wrong alignment, and this is just a very small representation, so that's just a simple PCA that is applied here, and obviously, so the red one are the target features, and the blue ones are the source features, and we are ending up with the wrong alignment, so that would not work for us. And for example, that could be our context that we have on the source. We have observed all the different fault classes, but on the target, we, for example, only observed just the healthy class, or that we observed healthy class plus one fault class. But that's the basic setup that we're starting with. And the idea that we pursued was not to align bilaterally, which is normally performed, but to keep the representation of the source of the source model, and to unilaterally align the representation of the target toward the source, so that we have one representation that is complete, and then we are aligning the representation that is not complete, and that one enables us to use also information on the classes that we have not observed yet. So that's what we're actually having here, so that we are keeping the representation of the source model, and that we are aligning the representation of the target data set. So how do we do that? So we train first the source classifier, and then we add an additional consistency loss, and the additional consistency loss penalizes the discrepancy to the features that were learned by the source data feature extractor. So we still keep the very same. We still have the classification loss. We still have the domain discriminator loss here, and we add an additional loss, the consistency loss, that penalizes for us the deviation from the learned feature representation of the source data set. And we first applied it on a benchmark data set, and the benchmark data set for the domain adaptation that we applied to is the NIST-M data set. So for the NIST, we have the black and white digits, and for the target we have colorized black and white digits. And what you see here is what happens if we start dropping out classes during the training time. We start first, so this is the case where we have the all of the classes present in the in the target and in the source. So NIST on NIST-M, and obviously they have the same performance. And now we start dropping some classes. So here we dropped 2 classes, here we dropped 5 classes, and actually until we dropped 7, it still looks kind of okay. But now we are starting dropping more or excluding more classes during the training, and now it starts decreasing dramatically. But if you look into the onto the green line, so this is so the performance still remains quite comparable to the best performance that we could achieve, and the best performance is here at the top, where we actually have all the classes present. So that's the comparison point, and it still achieves. So it does not. It starts not mixing the different classes and the representations as it's actually doing in this case. And we applied the same again for the fault classification task, and for that, so we did perform different combinations, and I'm just showing you here the case that we only have information on the healthy condition during training time. But we also did compare also what happens if we exclude the different number of classes and different combinations of classes. But what I'm showing you here is the case that so for the source, we have all the full classes and healthy class available. But for the target data set, during the training time, we are only using the information from the healthy conditions, but we are still testing the models on all the different full classes during the testing time. What you see here, so the baseline is the very same that you saw before. So this is the case when we don't do anything, and we are just so we have a model, and then we're just applying it onto the new data set under the different operating conditions. And for the unilateral alignment, we were able to achieve 98%. And if you remember, the best performing case where we had all of the different full classes present during the training time was actually 99%. So we are still quite close to this best achievable adaptation performance, given that we only have information on the healthy class here. So we are still improving it by 3%. And as already mentioned, I wanted to cover also a bit the case that we also need to deal with the case that we don't have any faults occurred also for the training data set. But we would still like to transfer the operating conditions for the new units, for example. So it sounds a bit strange that we would still like to transfer something because we did not observe any faults, and what we would possibly even like to transfer. But what we actually are trying to achieve is that even if we are applying a domain or an anomaly detector where we don't have any faults present, but on the target unit we did not observe yet all the operating conditions, we would still like this unit to perform quite well for the anomaly detection task. So before I start going into the domain adaptation part that was performed here, I need to give you a bit of a context, at least of how we were detecting anomalies. So it's not only us that are doing that, but at least to give you a bit of a context. So the basic idea here is that we have on the one hand an autoencoder, then we take the features of the autoencoder and we plug in the one-class classifier. We apply a bit of peculiar type of the one-class classifier. So that one-class classifier is not a kind of for the binary part, the binary type where we are distinguishing between the anomalies and the healthy class. So what it measures for us is the distance to the training data. And then it's a continuous output since we're just mapping it to one, and then we are measuring the distance to the training data. So that enables us not just to have the healthy or the unhealthy, but we can also distinguish how unhealthy it actually is. So that we can use it as a type of a health indicator, but basically it's really the distance to the training data. So the idea that we do there is that during the training, we are mapping it to one, so that represents for us the healthy class. And then with a small validation data set, we are adjusting the threshold of our output so that we are really matching it to one. And then after the validation part, we are starting monitoring it. And as you see, so this is the output of the one-class classifier. So it cannot be, the number cannot be interpreted directly. What it tells us that, for example, this part is probably more distant to the healthy class than this, less distant than this part, that probably here we have a second type of, or a more severe fault type. So that's how we can interpret it, but we cannot interpret the output directly. But what it gives us, to us, we can start monitoring how the health evolution, how the health evolves over time, and does not only provide us this binary information if it's anomalous or not. And the additional part on it is normally, so when we are detecting something here, so if we are crossing our threshold that we set, we are then going back and then we are looking into the reconstruction error, and so we are looking into the residuals, and the combination of which residuals are actually deviating provides us some information on what fault types this would actually be. So for example, if signal A and signal D are deviating, it could be fault type A, and if sensor F and sensor E are deviating together and sensor E is A as well, then it may be some other fault type. So that's how we, on the one hand, trying to distinguish the different fault types, but also trying to pin down which of the parameters are actually the most determining for the different fault types. So that's just a bit of the context. So that's not the core of the discussion or of the domain adaptation part here. But what we would like to do now is we would like to develop, so the basic assumption is that during the training time, we only have access to healthy data. So we don't have any faulty data, and this was as similar as discussed before. We cannot validate it actually on anything. So, and what we would like to do is we would like to transfer the operating conditions between different units. And for example, that's what we would have. And we could choose between different units actually. So this could be unit A, and this is our target, and this would be unit B, and this is our target, and this would be unit C, and this is our target. So the question is, on the one hand, how do we align? Because the classes and the labels that we had before for the domain adaptation, they act as kind of anchors, and then it's easier for us to align it to those anchors, and they provide us the structure in the feature space. But now we are really missing these anchors, and we cannot align it to anything here. I wanted to show you, or to show it to you in the context of a case study, and the case study was that we had 112 gas turbines. They were operated all across the world in different conditions. So some were really in very warm regions, and some were rather in colder regions. And 12 of those gas turbines had a fault, and there was in total 1 year of data that was collected from those different gas turbines. It had a 5-minute sampling rate, and we had 24 variables that were collected for each of the gas turbines. So there were some more, but these were the 24 were the common ones that were collected over all the 112 gas turbines. And that could be the challenge for us. So let's assume that we start with a very short observation time period. So this is, for example, one month here, or it could be 2 months, and our goal is to start detecting as soon as possible. So our project partner gave us this data set, and actually they were kind of testing us if we could detect anything or not. And the question was, can we detect something or not? And we don't know when the fault could be even happening. So the question is, which part of the data could we actually take there for training? Since we are for the anomaly detection, we assume that we are just taking the healthy part. So let's start with something small and then train our model, and then we could start plugging it in and then starting monitoring. So that very first part, so this the red one is the training, and the green one is the validation. So with that one we set the threshold, then we started monitoring, and obviously you see it starts really deviating quite significantly. Is it a fault or not? Well, obviously it's not a fault because we had some winter conditions there and we did not train our model on the winter condition. If we would extend our observation time period for 9 months, well, in this case, we are now not detecting anything here. We are covering also the winter conditions. But it could be also the case that there was some fault occurring here, and we would have actually used it for training because our model is only measuring the distance to our training conditions. And if we learn the fault, we will not detect the fault as well. But in this case, it worked at least quite well. We could start detecting something at the very end. And actually, all of the units were having faults at the very end, but we were not told that at the beginning. But now we start also detecting when there is something to detect. And the question is, so shall we take the whole year, or how can we perform with that? Another approach that we also did is we did combine all the 112 units, and we trained we trained a model on all the 112 units, and obviously it was not detecting for none of the units. So for some it was not detecting anything, and for some it was detecting then too much because it's not adjusted to the specific operating conditions of the unit. So what we would like to achieve is, on the one hand, to start monitoring the unit as soon as possible, but on the other hand, to make sure that the model that we are using is as representative as possible for that specific unit, so that we are not missing the faults, but on the other hand, that we are also detecting the faults when there is something to detect. So that's a bit the balance to find, to be sure that we have a good model that will also perform on new operating conditions that we haven't seen before, but also that we are not detecting unseen conditions as faults. And since we don't have any anchors, so any faults in our data, we cannot use them for training at all. And the idea is, so the question is, how can we actually align the data from the two units? So we have the source and the target units here. So that's our source and target healthy features, and that would be our source and target anomalies. And if we just align them naively, well, we would not detect anything in this case. And this is the ideal case that we would like to achieve. And the idea behind it, so how to achieve that, is to keep the inter-sample relationships. So what we had here is as similarly as was presented before. So we still have the feature extractor. Oh, sorry. So we still have the feature extractor here. That's similar to the case for the domain adaptation with the folds. And we still have the domain discriminator because we still have the two domains, but we don't have any fold, any classifier loss. So this part is actually missing for us. And since we have just one classifier loss, so that is not working for us. But what we added additionally, so we still have that part and we still have that part in our loss. But what we added additionally is this scale domain adaptation, so that we enforced a scale projection between the input and the latent space, so that we enable it to be rotated or to be scaled, the representation between the input and the feature space, but to keep the intersample, the pairwise intersample relationships. So that is the idea behind it, that is what we actually then applied. So we had the three parts of the loss, and that's what we applied then on the case study with this 112 gas turbine. And for example, this was the case where we just used the source, the target unit, and we just trained it on this 2 month of target unit, and obviously now it started deviating here. And now we enrich this, this target unit with a representation, with the aligned representation of more experienced source unit. And now we started not detecting anything here in the meanwhile, and we started detecting something when there is really something to detect. So that really helped us to enlarge the operational experience of the different units in the fleet, and really to start detecting more robustly in our case. So with that, I was giving you some insights into the domain adaptation for fault diagnostics. So that was the first case where I was showing you how to use the information from the source data set that is complete, but also to adjust it to, or to adapt it to the target data set that is also complete in the sense that it does contain all the different fault types. I did also show you a case study what to do if we have some missing classes on the target data set, for example, that all the fault classes would be missing. And the last case study that I was showing you was domain adaptation for the cases that we don't have any faults observed at all, that we only are able to use the healthy data. And with that, I would like to close, and we still have 15 minutes for questions. And if there are no questions, you can have a larger break, since we already have taken away the other break from you. I don't have access to Volvo, so if there are any questions in Volvo, I'm sorry, maybe someone can pass them on to me.
Thank you very much, Olga. Very interesting presentation. We have one question in Volvo. I don't know if the person who asked it can ask it directly here, or if I should read it.
Yeah. Can you hear me?
Yes.
Yes.
I hear you.
Yeah. I'm Uta. Yeah, I have a question, and this is related to your last slide with a health monitoring approach. So I was wondering if your approach can be applied to structural health monitoring, for instance, for bridges or windmills, because I guessing that compared to machine in a production process, we cannot get the data sources, or it's difficult. We have only the healthies, or more or less healthies, not so much examples for faults.
Well, actually, in fact, we have currently a student who is working on the structural health monitoring. However, he's using lab data, so collected experiments. But here we don't have faults at all. So and in fact, for this for the 112 gas turbines, we had only 12 faults. And we did not use this faults at all for training. So our task was really to find the units that failed. And so we are testing right now also the transferability to the structural health monitoring. And we believe that it's quite promising there, and it does have some potential, obviously, because it does not use any faulty data for training it, and we could benefit from different types of structures, and that's actually the nice part. What we don't have here yet included is the prediction of the remaining useful life. So that's also a bit what the master student is currently looking into, how to also apply it potentially to the remaining useful life prediction. But that's a bit kind of the final goal. So even transferring between more experience or units. So that is what would be already quite nice results.
Hi, Olga. This is Anjan.
Hi, Anjan.
Hello. Hi. Thanks a lot for this great overview. I really like the talk, domain adaptation. It's very much in line with our work here at ASML. A question. It's a very nice overview, but I would like you to discuss about the limitation of the method. How long or how far can you stretch the domain adaptation?
Yeah, that's a very good question. This was a bit on our agenda to see how dissimilar the domains can be, that we still can align them. So the nice part is that we are only performing their alignment in the feature space. So this is really the key success factor here. But one of our goals is to apply domain adaptation even between units that are monitored in a different way, so that where even sensors are not the same. So the idea is then to have the feature space similar or have a similar feature space, and then to start aligning from there. So we are not there yet. But this is one of the goals and one of the directions, or one of the ways that we were thinking of how to be able to achieve it, to integrate some type of physical relationships in the feature space as well, and then to make this interpretability in the feature space. And with that, we can have a representation that is physically interpretable in the feature space, and then we can start aligning. So that's really a bit the future direction. We are not there yet, but yeah, we believe if it's possible to do that, that would be really promising. Did it answer your question?
Yes, thank you.
I have a very practical question. You mentioned the bearing data set from
Yes.
Case Western Reserve University. Is
Yes.
that available? Can you post a link?
Yes, so this is, you can just drop me an email. So there is, so on the one hand, it's openly available. It's not our data set. We also took it from somewhere. But if you're interested in more data sets, I can also pass on you some of the links, because we are also collecting links to openly available data sets. But maybe you could also specify what specifically you're looking for, because by now we may have some collection already, yeah.
Do you? I posted a link into the chat of Zoom, which I found. Maybe that's the data set already. Do you have a list of the links which you just mentioned online, or do you just have them on your computer?
No, we just collected them for the team.
Okay.
But for example, I don't know if you're familiar with the NASA dataset repository. So they are collecting it as well. It's not that all of the datasets are available, but the dataset that we have made available is a dataset that was collected by Airbus. So it's accelerometer measurements. It is also for anomaly detection. So that one we have uploaded. I can also share the link with that. We have been also working recently on predicting the remaining useful life. And if you're familiar with the CMAPS data set that was posted by NASA some time ago, we have developed or have generated new data sets from that. So we developed it a bit further. We have not, so that one we have not yet released, but we are planning to release it soon for the remaining useful life prediction. So yeah, I will be happy to pass on those that are already available, but also we are planning to release some additional data sets in the near future.
I will drop you an email. That sounds great, because that is a real bottleneck for me as a lowly PhD student.
Yeah, I actually have it for the Outlook. So this is the part for the Outlook, that actually one of the key limitations of the community is that we are lacking benchmark data sets, and the benchmark data sets that are used are not that suitable. And actually the CWRU data set is known to be highly overfitted, and it's known that there are a lot of falsely classified patterns as well that are then learned. But that's the data set that the community is using. So
okay,
we used it as well.
yeah. Well, you have to start somewhere, right? So.
Yes, and also there was already a case study that was published on that specific data set. They were applying domain adaptation, and so we wanted to compare to them as well. So that was also the reason that we selected it.
Thanks.
Hi, Olga. I have another question about the practicalities. You have mostly time series. I think also in the case of the previous presentation, Slawomir presentation as well. The question is, you have to choose certain aggregate windows. Do you use it as a hyperparameter in your model after building the models, or is there some domain knowledge going in the time windows? How do you discretize your data?
So actually, those that I was showing, we were just using the information on one time step. So we were not using the past time windows. So we were not using the information, the time, the evolution on time. At least for those case studies that I was showing. For the vibration data sets, yes, obviously you need to define the time windows. But for the other data sets now, what we are looking into, for example, we are applying CNNs for time series data. And one of the challenges there is that you need to choose the length of the time series that you're considering based on the time how do you call it, dependencies that you would like to detect. Because, for example, in the case study that we were applying it to, so this was particularly for the remaining useful life prediction, and there you would like to see also longer time dependencies, so not just the short time dependency, but longer time dependencies. And this started to be a bit challenging to decide about what is the length of your time window. But what we saw was that particularly for those prediction of the remaining useful life task, it was useful to increase the time window, because we started to capture also the dependencies over longer time periods. But then it starts to be computationally a bit more heavy. But that's a bit of domain knowledge. So what type of time dependencies do you expect in your time series data? So we are not subsampling actually. So it depends actually. We also do have some cases where we have different sampling rates. We do that as well. Yes. Did it answer your question, Anjan?
Yeah. I'm curious about now you mentioned 2 times about the remaining useful time models which you are looking into it. Did you already publish that work? Can I find the presentations on your website?
So that's actually the work that we did with hybrid approaches. So it's the paper that so it's still an archive, but it's a paper on fusing. I don't remember exactly the title, but it's fusing physics and deep learning models for remaining useful life prediction. So that one is on archive. If you send me an email, I will be happy to share the link. But we're actually currently revising the paper, and in that paper we also included the CNN. So the current version of the paper only has the feed-forward neural networks included, but in the revised version we will have also the CNNs included with these different time windows as well.
We'll do that. Thanks a lot, Olga.
Thanks for the interest. We have 3 minutes left, but we can also really go earlier in the coffee break if there are no more questions.
Any one final question, or one and only chance?
If that's not the case, thank you very much for attending, but also for asking the interesting questions. And yeah, see you at the end of the tutorial.
So welcome everybody to the third part of this tutorial. Now we have Jessica, who is going to tell us a little bit about how those things we talk about in very theoretical fashion actually help us in real world or in the industry. Welcome.
Thank you, Slawomir. Thank you for the invitation. I hope everybody can hear and see me now. So I work at Truck Monitoring Center at Volvo Group, where we apply machine learning models, or artificial intelligence, how you want to call it, to avoid that trucks come into a breakdown that is unexpected. Why isn't, yeah, okay. So after the previous two presentations, you can say, okay, you can model data, great. However, it's a whole different setting when you want to use that model that you created to a data service around it. And that's actually what we have been doing at Volvo, and where we actually saw that it's not the modeling part that is most challenging. It's actually putting it into production and building an entire data service around it. So on the agenda for the next 45 to 50 minutes, depending on how long it takes for me to explain everything, I'll explain what do we do, how we are doing what we do, and where we're headed toward the future, and some main conclusions. So first of all, what does TMC do? We all know transportation is crucial in current society, and we monitor trucks. And that's quite important. Why? It's because monitoring trucks, even though to me, I came from a computational neuroscience background, it seemed like a bit less relevant for our daily society. It still makes your life better. How? Imagine you have a boyfriend, your boyfriend's a last-minute birthday party. Thank God you have online shopping, and certainly in times of Corona. How grateful are you when your present for your boyfriend is delivered within 24 hours? However, shit happens. What if the truck that was supposed to deliver your present within 24 hours breaks down? That's actually where we come in. Of course, Volvo doesn't really care about the fact whether or not you got your boyfriend's present on time, so we don't really care about your relationships. We don't, actually. We care about our customer. And for our customer, time is money. Meaning, if they don't deliver in time, whatever they have to deliver, they often have to pay fines. So they want to avoid being on the side of the road. And that's where we come in. We are a breakdown prevention service. By applying artificial intelligence to real-time data sent from the trucks to our service here at Volvo, we actually run our models of predictive maintenance to see whether or not there will be a breakdown in the next month. With this information, the customer can schedule an appointment to the workshop to repair that specific component or part of the truck that will have a breakdown. And that way they can schedule it in a moment that is most suited for them, meaning not when they have to be on the road and manage to get their deadlines, but in between different deliveries. In short overview, how do we do that? The data from the vehicle is sent around the clock to our servers, and then each time, well, every 2 hours, we run all our models, and then we can predict for each truck we have in our fleet, so for all the trucks we monitor, whether or not there will be a breakdown in so many days for which specific component. At the moment, we have prevented about 16,633 breakdowns on the road. This might seem not quite a lot, but it is for us, as we only started 3.5 years ago. So how do we do this? How did we manage to build these successful predictive models and put it into an actual data service? I'm going to first touch upon the history. How did we get to this point? Because the history, we're still dragging some legacies because of the fact how we started 3.5 years ago. Also, it's very interesting. Well, was one of the reasons why I wanted to work here is which kind of data do we use? Because all the components in a truck are mechanical. An engine, how do we go from an engine to digital data, which we can then use to model? First, and thirdly, how do we create the models? And then once we have the models, how do we visualize our core business? How do we deliver this information to our customers? And also as a fifth, how do we make it operational? And it's actually these fourth and fifth points that costs us most time. First, history. So we lifted off somewhere at the end of 2016. And actually at that time, there were only 2 people working part-time, and I still find this quite strange. It was an entire manual process, meaning they pulled in from 600 vehicles, all the data into an Excel file, imagine that in 2016, and they went through every vehicle for one component, the battery in the truck. And those 2 people just went line by line in the Excel file to check whether or not there was something strange going on, to then manually send an email to that customer. So that was 2016. At the moment, we monitor about 56,000 vehicles for over 10 components with only 12 people. And instead of doing only 1 time a day, a manual check on one component, whether or not there will be breakdowns on a component, we do it now every 2 hours. For that, we had to create an entirely different setting. So no Excel sheets anymore. And we needed to create an entire IT environment and an entire data engineering environment to actually be able to do that. So this is just a short overview. We have a data lab where us as data scientists can do whatever we want without breaking down, and this is a very crucial part, without breaking down the production process. Because, for example, let's say I want to run a model and it takes for 3-4 hours to actually run the model and take a lot of resources off the servers where we're running it on. You don't want to, you want to avoid that mere running a very large analysis blocks the ability to run our models in production and to actually do the service. That is separated. All the data that we're using are refreshed quite often, and it's a very good environment at the moment to be in. Okay, so we came from there. Manual process for just one component. But what kind of data do we work on? How do we go from a mechanical system like an engine to actually predicting that a subpart of that system will break down in 3 days? For that to know, you need to know that actually within the engine, there are a lot of sensors. Each sensor calculates different things. For example, inside the engine, there is a sensor that measures the temperature. There's a sensor that measures the vehicle speed. All these sensors together create a lot of data that all has been sent to sort of a mini PC, an electrical control unit. That electrical control unit has software installed. that software is programmed to know, okay, let's say that the temperature of the engine has arrived some sort of critical level. It will create a sort of fault code. We call these fault codes. Why? Because it's always, this code is created from the moment on. Some engineer at Volvo has said, like, if that passes that critical level, we need to create an alert. These alerts, you know them, because some of these alerts will create this dashboard lights that you see, and which I tend to ignore until the moment I'm on the side of the road. As a typical woman, I think that this is not relevant, these lights, but I tend to ignore them. Anyway, they're quite important. Of course, not all fault codes generate lights on your dashboard, because then you would have a Christmas tree all year round. So thank God that's not the case. Here at TMC, we tend to use only the fault codes that does not light up any of these dashboard lights, because these dashboard lights give the information already to the customer. There are about over 100 of ECUs in one truck. All of them create many, many fault codes. All of them are sent to our servers. So that's the input data we work on. We don't directly work on the parameters, which is, for example, the engine temperature. We work on the parts that are behind it. The reason for that is we are restricted by the technology that's installed in the truck, the TGW, so telematic gateway. That's the unit that actually sends data through 3G to our servers. We cannot send all data at all time, because there's no way it would be able to do that. So that's why we work on these summarized fault codes to actually be able to somehow do some modeling. Of course, me as data scientist, I would prefer to work on the raw data, but unfortunately, we don't have many of them. So that's the input data. How do we do the modeling? So how do we go from these fault codes to an actually breakdown prediction? I can skip through this a bit more faster, because you're all machine learning experts. And as you all know, before we can do any modeling, we need to do data cleaning. And hopefully, well, not hopefully, I hope for you that you don't have the same amount of data cleaning to do as we here at Volvo. I must say, when we're actually modeling, about 90% of model development goes in data cleaning. And the reason for that is a lot of the data that we're relying on, besides the fault codes, are actually manually put in by, for example, people who work at a workshop, at a garage. We need to know what happened to the truck at what point to be able to model. And that's all put in free text or with some generated codes, but it's all manual process. Therefore, it's messy, very messy. On the other hand, also, at some certain points, telematic gateway, so the thingy that sends data through us, doesn't work properly, or the truck has detached that part of the truck, or it's broken, whatever, we have shitty data. So a lot of data cleaning. How do we actually do the modeling? It's actually quite simple, the principle by itself. As you know, you need a target. What we take as a target, let's say we want to create a model for the AdBlue pump, we take as time 0 the actual repair to the AdBlue pump for a truck, and now we look at 2 months before that repair happened, what type of fault codes came in. Of course, there are a lot of them, and very important here is again the distinction between building a theoretical model and building a model for production. As a theoretical, when I came in here, I thought, well, let's use all the fault codes that come in and the classifier will do its magic trick. Who cares how long it takes? Well, in production, you do care how long it takes. It has to be fast enough because you need to process a lot of vehicles in a very short time. Because for some of the components, it's very critical to know when it will happen, and it's rather sooner than later. Therefore, we need to do feature selection. We also tried many things there. We tried a lot of algorithms to select out those best features. But actually, the ones that are helping us the most are technical experts. So, and I didn't also, I trusted more algorithms than I trusted a human being before I entered here at Volvo. But apparently, the human beings here are very, very crucial for the modeling job. Because it appears to be when we, for example, give all these fault codes that came in 2 months before that, you do some basic algorithms, you pick out the top 100 best features, you give those to a technical expert. A technical expert is somebody who knows that component very, very well. And they go through it again. And they can tell us like, oh yeah, it might be that this fault code is reoccurring quite a lot, but actually it has nothing specifically to do with that component, so ditch it. And that's how we actually do the feature selection, is based on algorithm together with human knowledge. The actual modeling done itself, you create for, you know all this of course. We then take during our training session, we take for each truck, we take the feature vector, we look at which fault codes happened, how many times 1 day before the repair, we look at 5 days before the repair, we look at 7 days before the repair, and so forth. This is our training set. Then in testing, we give the model, the trained model, again, all the feature vectors of different trucks which are not being used in the training, and we ask the model to estimate how many days it would take until this component breaks down, and you calculate the model performance. This is a dummy example, so forgive me for the very, very low-level presentation, but I don't want to get into this too much because you have to do best persons before this to explain you all the nice and neat tricks you can do for the modeling. For predictive maintenance, I'm going to mainly talk what to do once you have that model. Just to be clear, we use several algorithms. Weirdly enough, the XGBoost tends to be outperforming often other algorithms, and not really, because we always need to choose between accuracy of the model and speed of the model. So that has to be in balance. You cannot, even though if we would find a model that's performing 10% better than another model, but that other model who's performing less is much faster, we will tend to choose for the faster model. Again, very weird as data scientists to do that, but it's business. You need to make sure that your business value is big enough. Once the model is in production, we get to this. So every 2 hours, we run on our entire fleet, all the models we have to make predictions on our fleet. Of course, once you finally have a model that is in production and it's working great, you should know, and was talking about the ECUs, so the electrical control units, which has software installed. Well, as all softwares, it's not stable. So it might be that some person who is developing the software changes the moment where the fault code is sent. For example, let's talk about temperature again in the engine. In the previous software version, it might be have set at 70 degrees, and the next software version is 90 degrees. However, the most important thing might be that at 75 degrees, we already know, well, this component is going to break down in the next 30 days. But when the software changes, the fault code doesn't pop up anymore at 75 degrees, but only from 80 degrees on, meaning that our model becomes less sensitive. So we need to retrain these models every once in a while. Not every once in a while, quite a lot. However, in our fleet, the problem is when you want to retrain, you need repairs again. You need to know, okay, this time 0, these are the fault codes that happened. However, if we're sending cases, so if we're saying for our fleet, okay, you need to do a repair now, the time 0 shifts up, and you don't have the entire overview of the feature vector anymore because you're intervening in the time 0. So therefore, we created 2 fleets. One fleet, we call it our active fleet, and the other fleet, we call it our passive fleet. For our active fleet, we collect all the data, we send out cases, we cost repair. So this is what our paying customers get. On the other hand, in our passive fleet, we still collect all the data, we still run the models, but we never actually send a case. Therefore, we never cause a repair. And that's what we call our virgin fleet. We never touch them. Therefore, we can use only our passive fleet to retrain the models. they should again be large enough because we need enough data. And actually, that's a huge problem, not only for when the model is in production, but also for creating the model. As I said from the beginning, the data is messy, meaning we have a lot of problems. We have this Volvo repair system. It's called VSR. And that's where actually most of our workshops, and remember the word most, actually log in when there was a repair to a certain component for a certain truck. However, for example, for one of our brands, Renault trucks, they don't use that. Each workshop uses their own system, which we cannot use. So therefore, for a large part of our trucks, we actually never know this time zero. Also, enough frequent data sent from the truck is necessary. As I said, the DGW often doesn't work, or works, but not for everything. So often we don't have enough data to do machine learning, but our markets request for us to actually produce a model. And then again, truck experts. So here at Volvo, I often feel like they're the heroes and I just do whatever they say I need to do. So truck experts to the rescue. And instead of letting the machine find the pattern to predict, we use a human being who has all the knowledge from the trucks to define which fault codes are crucial and at which level they will lead to an unavoidable breakdown. And it's actually a very straightforward decision tree, a decision tree that's created manually. And it's, for example, an example. This is only for one fault code, so this is the most basal model we have, expert model we call it, model we have, and it just checks for several conditions, whether or not there should be a case sent for, in this case, a fuel case. Why not always use an expert model? Well, as a data scientist, I would say I trust, again, algorithms better as human beings. Mostly the reason is it takes a lot of work. This previous model that I've shown, it looks very simple, but it actually takes longer work than when you do machine learning, because they need to dig into the data quite deep. And they need to get in touch with all the people who create a sub-part of the software on the ECU, and to get to know better and better how that actually component works. And that's not easy to do. So we tend to first always see whether or not we have enough data to do the machine learning before we move to an expert model. This is an overview of all the current models we are either having in production or either developing. So there are quite a lot at the moment. And for next year, there are 4 more new ones to be added. 4 doesn't seem too much, but you should know it takes about 6 to 8 months of full-time work of one technical expert and one data scientist to create one model that's production ready. So 4 is quite good. So, okay, we have our model now, yay, but how to go from a model to actually practically using it? Because you now have this model that's shooting every 2 hours, like, okay, this truck needs a repair. Awesome. But you're in a big company. You need to make sure that the communication is done. You need to make sure that it's optimized. For example, we launch thousands of cases per month. You don't want to manually each time look up for that vehicle, who is the contact person, and send out a mail to that contact person. Also, the workshops, they need the information for that vehicle. So everything after you produce the model, it's not finished at that moment. And that part is a lot of optimization. Also, you need to have some insights in how well your service is doing. So KPIs need to be calculated. Also, everything lies with us. So how do we visualize our core business? This is a very old dashboard, which we're still using. But in the next few months, we will transition entirely, going from ClickView, it's called. I never had heard of it before. So it's something like Power BI, but from ClickView. And we're recreating these entire dashboards and all the KPIs behind it to a Python environment, to create our own, where we can tweak whatever we want, however we want it. So this is for us and for higher management. This is for internal use. On the long end, we want to create individual dashboards for big fleet companies. Big fleet companies, what are they? Those are like large companies that have like hundreds of trucks in their portfolio, which they monitor to do the transportation, and they might want to get some insights. So in the long run, we want to also create these individual dashboards per customer with all the information they want. So therefore, we're going away from ClickView and moving into, well, not Power BI anymore, but entirely into Python and using Plotly. Because with Plotly, you can create interactive dashboards, which is pretty cool. So we're working on that as well. And it's also very easy to create dashboards that are online available and where you can log in via API and so forth, also to do with Python. For now, every time we send out a case, because this is just visualization for us, we also need to make sure that the customer is warned. So after the model triggers, says like, this truck will need a repair in the next few days to this component, there's an automatic PDF that is being created with all the vehicle information with the description of the problem. This description of the problem is in the language that is native to the country. For example, for England, it's English, but for France, it will be in French. For Spain, it will be in Spanish. The reason why is because people working at the workshop or the truck driver often don't speak well enough English to actually read what we are sending. So we have also a translation team who is working for us, where we send out all our templates for the problem description. There's also an automatic mail with this PDF then included is being sent to the person who's responsible for that vehicle with all the information in there, again in the language of what they're using. Okay, so we need to do this quite often, every 2 hours, but we don't want to keep working every 2 hours and sending all these cases. We also need to have our entire system where we keep track, okay, who is our customer? Who is behind it? What is the contact information of that person? And so forth. So one of my colleagues here started in his own free time at the evening thinking about this, and he never had written any words in Python before, and he started to build an application in Python, an application we call the Monitoring Service Admin Portal, where we actually do everything. There's a lot of data engineering behind it that he manages together with now another colleague, but everything is in there. Also knowing which kind of components are open to which markets. Because, for example, it might be that Renault in France only is willing to pay for the battery and for the TPF component, but Volvo in France is willing to pay for all 7 of the components. So therefore, we need to know when our model shoots like this vehicle, it needs a repair. We need to check before we send out a case whether or not for that component that customer is paying for. If he's not paying for it, he's not getting the case. All of that is managed through MSAP, so the Monitoring Service Admin Portal. And we're also looking into, as I said, our dashboards are now being created in ClickView. So this is just a very ugly template of a dashboard, but we're trying around to get everything into this MSAP so that, for example, customers in the long term could log into MSAP and see their entire own dashboards. What about the future? Because this seems like we're getting everything we want and it's going very smoothly. Of course, you're talking about data, you're talking about data science, you're talking about data service. Not everything is as good as it seems from the beginning. So where are we heading? What are the things that we need to work on further in the next 4 to 5 years? First of all, we're pushing the limits of our servers. You need to know there's a lot of data going around. We need to pull them. They're now on the local server in our company. It's getting fuller and fuller, so there are often problems with running our models in production because there's not enough space to run them anymore. So we're killing the server slowly and slowly. So therefore, we decided to move our entire system to either, well, it's still debated whether it's going to be a Hadoop on-premise solution with extra additional servers or either cloud environment. It will take up an estimation of about 6 months of work of most of our team to make everything operational again. Because we need to readjust all the models to new tables, in a new environment, there might be not all the data available we're using now for the modeling and so forth. Also this case sense automation and so further, it all needs to be readjusted. We need to do it because we're killing the system we're in it at the moment. So there's no choice, but it will take a lot of time for us. Also, as I said, very important to know is we have a legacy. At the moment when this team started 3.5 years ago, there was nobody who was able to program. So no Python. What was the solution? Was SPSS Modeler. It sounds as awful as it is. As a data scientist, it's a drag and drop nodes where you actually pull in the data and then you pull a node like, hey, I want a neural network on this data set. It's a very big black box. But it's for legacy reasons, we're still working in this at the moment. But once we made the transition to our new server, I pushed quite a lot for that, we will finally be able to develop everything in Python and put also the models into Python models into production. And for me, that will give a lot of freedom to us data scientists, because working as SPSS Modeler, it restricts what you can do. It's quite a black box, meaning I don't get to do these nice figures to look into all the features and all the parameters of the machine learning classifications. Also, you're restricted in the type of algorithms you can use to the algorithms that are actually stuck in SPSS Modeler. So what we often do now is we create some tables and we have our local Python on our PC where we do the fancy stuff and we get a very good model out of Python, and then we want to transfer it to SPSS and it all turns to shit. So yeah, very happy that's going to be happen, because we can actually do optimized algorithms to do the feature selection even more and data cleaning. Also, there's no time series node in N2 SPSS, or no survival analysis node in SPSS, and it's actually 2 new algorithms, well, not new, but relatively new for SPSS, that actually might serve very, very well for predicting whether or not a component will break down. So it's also something, well, we already explored it. It works better than the algorithm in SPSS. So very happy if we can use it into production. And most of all, get away from the black box that SPSS Modeler is. And also good to know is it will be very easy, as our entire monitoring system is in Python, to actually pull everything together into MSOP. Also, as I said, we're quite a lot missing data. So for example, if some markets do not use the system to log the repairs, so we're looking for alternatives, either via algorithms to see, for example, if a certain fault code is increasing over time and then suddenly drops, that might be because there was a repair to that component, because normally fault codes don't drop that sudden. So we're now exploring whether that could be a very good simulation, well, a very good estimation, or whether or not there has been a repair to that component. And sometimes data is not good of quality. So for example, the total mileage, that should be increasing every single day the truck is driving. But we see that often it drops back to 0 and then restarts again. So we have to look for ways to solve this data that is not logical or not correct. And also, even though we have optimized quite a lot already, it still requires quite some manual labor. So before the case is launched, there's still a technical expert going through some minor details. It only takes minutes per case, but it takes minutes, it shouldn't be there. But therefore, we need to hack into one of the systems at Volvo, the IT systems, to actually be able to automatically create this case in the Volvo system. And therefore, we need to work with IT, and it takes some time to work with IT always, because they're very highly demanded. Also, after the case is launched, we need to follow up the case, because you can say like, oh yeah, let's shoot cases, but you need to know whether you were correct or not. Was there indeed a needed repair to that component when the truck came to the workshop? We're following that up now. It's 70% optimized, but as I said, a lot of some workshops don't use our logging systems for the repairs. If they don't use the logging system for the repair, how the hell are you going to know whether that repair happened or not after you launch the case? We have a call center calls. So we need to find a way to avoid that as well. And also there's a lot of free texts in there that we use to find certain repairs or certain things. We're now looking into natural language processing to also automate parts of that. And also Volvo Group, which surprised me as much as it might surprise you, or I hope it might surprise you as much as it didn't to me. It's more than trucks. It's also Penta, and that are, for example, units, generators for hospitals, engines for boats, for airplanes. We also have buses. We have our entire e-mobility track. And all of these stakeholders are coming on board on TMC. And that actually creates new challenges. Going from, for example, with Penta, they almost have no connectivity on generators in hospitals, but it might be quite crucial to know when a generator, backup generator of a hospital breaks down. But if it's not sending data, how will you do that? So we need to work together with the technology department to actually make sure that we will be able to do that, which creates a lot of new challenges, which is kind of fun, I think. So as a summary, we're a truck monitoring center, and we give a breakdown prevention service based on real-time data. And I think the most important thing to take away here is well, at least for me, that was a big lesson. Algorithms cannot solve everything. You need some human knowledge as well. And as I don't know anything about trucks, I'm very lucky to have colleagues who do know everything about trucks that they need to know. And also we are an all-in-one 24/7 service. So we're developing the models, but we're also building everything next to it for the service, going from data warehousing to actually communication with the customer. And if you ever want to build a data service, don't just look for the best data scientists, look for people who can also build everything behind and next to the modeling itself. So I think I made it quite in time. If there are any questions, please feel free to shoot, and I will be happy to answer them. Thank you for your attention.
Thank you very much, Jessica. Really interesting presentation. And we already have a whole bunch of questions in the chat. I guess you can chat here, so maybe that's the easiest. Or if people can just ask them with voice.
Yeah, well, I'm going to open the chat. How did you set this -2 months time window? Did you play around with other time windows? Yeah, the reason for the -2 months is actually service related. Our service promises to avoid breakdowns in the next month and maximum the next month, not over that. Because over that, there's another service at Volvo who is doing everything from 1 month on to all the rest. So we might want to take a longer time window, but that's actually not necessary because 2 months in advance is more than enough for the 1 month that we have to predict in the beginning. So I hope this answers your question. The vehicles in the passive fleet are those that didn't opt for predictive maintenance, or how do you decide on that? Well, those vehicles in the passive fleet are the ones where we're GDPR-wise are allowed to track and monitor all the data, but they indeed did not choose for having predictive maintenance. There's one small problem with that, is the fact that our passive fleet is not entirely it's representative, but not as representative as I would want it to be, as most of them opt for predictive maintenance in the first few years of the truck driving around. The older the vehicle becomes, the less they tend to do costs on it. And I think if you own a car, you have a similar reason. You take an all-in insurance for the first 2 years, for example, and then after that you think, well, if I drive into a tree, who cares? No. Anyway, it's actually the ones that didn't opt for predictive maintenance. And the fact that it's not representative is not that bad because we want to learn from the past. And let's say that our passive fleet was also only 1, 2, or 3 years old of the truck driving around. That means in the first 3, 4 years, a truck doesn't need that much repair done. Because it's all very new. So then you would still not have enough repair data for modeling. So In one way, it's not very good. It's not very representative in terms of age compared to our actually active fleet. But in the other way, it's actually what we need because it shows us the future of our current active fleet. I hope that's a bit clear. Next question from Richard. How many are in the virgin fleet and how many are in the active fleet? It's about half-half. So, well, not entirely anymore. So it's about 30,000 in the active fleet and about 25,000 in the passive fleet. We tend to not need to increase the passive fleet anymore because the cost of the passive fleet is entirely driven by Volvo. So because sending each data point from the DGW, so from the thingy in the truck that sends data, it actually is some cost for Volvo. So we need to decide when the passive fleet is large enough to be able to retrain our models and to be able to do some investigations in that without driving up the cost too much. And for us, at the moment, we actually are quite happy with the size of the passive fleet. On the other hand, the active fleet is each time, every week, it's increasing with about 1,000. So 1,000 contracts are sold for the predictive maintenance. So it will tend to skew up more and more actually over the next few years. Another question from Min, how to evaluate the number of failures being effectively prevented? If we intervene and restore the truck's health even before a failure occurs, how can we be sure we've prevented the failure or whether it was just a false alert? Well, that's indeed one of the core questions. Luckily for us, when we send out a case, it's not that the guys at workshop who are doing the repairs are actually not looking at the components anymore. They do investigations, like when you would go with your car to a workshop. I hope that they just don't blindly replace the battery, which costs quite a lot, without having a look at the battery, whether it's indeed going to fail. So we have this reassurance that when we send out a case and the repair is done in a workshop, we kind of trust the guys that are working in the workshop because the components we're monitoring are often not that cheap. So they will not replace it whether if there's not something that's a problem. But there is a problem for the moments where we cannot communicate, well, when we send out a case and we cannot reach the customer or whether it's not logged in in the repair system, then we're not sure whether or not our case was successful. And therefore, again, we need to look in how to know when there was a repair, when there wasn't a repair at all. And that's one of the most challenging things what we are working on at the moment is trying to see whether or not there was a repair by, for example, the fault codes that are dropping. But you should know that that's not ideal. Why not? Because we have fault codes that are self-healing. Some trick from the software engineers that apparently some fault codes, when they increase and there's a bit stable at a certain point, they reset them automatically to 0. So there wasn't a repair, but the DVC dropped anyway. So that's a very big challenge to do that, actually. Another question from Stefan, how many truck components are monitored if I would buy the whole package? At the moment, 10. So, but how did we decide on those 10 components? We actually looked at the breakdown lists, meaning what components cause the most breakdowns on the side of the road. So which breakdowns actually caused that the truck driver had to call a help system like, hey, I'm on the side of the road, so please come and tow me away to a nearest workshop. And then we look at which component was responsible for that. So, and we just went down from 1 to 10. So we're now at 10th on the list of the breakdown. Richard asked, what's Hadoop? Isn't Hadoop pretty much superseded?
Not what is Hadoop? I know what Hadoop is. I know
why Hadoop?
I mean,
Unfortunately, I have my own preferences for the system I would like to go to as a data scientist, preferably something that you can just buy quite easily, a new space. and which is a bit more efficient as Hadoop. But I don't get to decide that. So one of the reasons Hadoop is still in the picture is because our IT department invested quite a lot 2 years ago in an entire Hadoop environment premise. And there's a bit of a discussion going up way above my head where we should go to. So, okay. Yeah.
Because Hadoop was already superseded 2 years ago by Spark, for example, and other technologies.
I know.
Hadoop has been old for at least 4 years. Yeah.
I know.
Okay. Okay.
I couldn't agree more. So,
okay.
And SPSS Smaller was superseded ago already 20 years ago, but somehow we're still working in it here at Volvo. So I'm not sure whether you work at a company or not. I used to work at the university.
Both,
and
yes. Both.
Yeah.
I work in a company and not. I work part-time at university doing foundational research and part-time in industry. So.
Yeah. And I'm not sure whether you already saw also the differences at the university. You just pick out the ones that are just brand new and you want to try them out. And certainly in a large company like Volvo, you don't get to do whatever you want. Until a year ago, it was not even very supported that you use Python on your local PC. So in that way, Hadoop is quite new for Volvo. So yeah.
Yeah. No, I understand that. I have also worked with Hadoop while it was already legacy. What is really depressing to me, but I understand that sometimes people don't listen to the data scientists who actually know best. What is depressing to me is if a system is introduced which is already legacy at the point of introduction, that I think is really bad. I mean, if you have a system and it becomes legacy and it's hard to replace, I get that. But don't introduce a system which is already legacy at the point of introduction. That is just stupid.
Yep. That's exactly my words to my. I put it even more blunt to my boss. So you're still quite polite. So I gave my same opinion to my boss, but apparently he has no say in it as well. So it's I have to wait what the verdict will be that's being decided for me. So
realistically, there is also another perspective, because yes, we data scientists always like to go for the newest, shiniest tool. But there is also a little bit to be said about maturity and the bleeding edge of the software.
That is
for example, the same.
There are other tools which are mature and have superseded Hadoop. I mean, Hadoop is not just superseded by new in the sense that there's new and shiny stuff which is bloody edge and doesn't really work stable, but it has been even superseded in the sense that the stuff that supersede Hadoop are stable and mature. So that is the point. I mean, even from
this presentation is being recorded, isn't it? So can I use this discussion to send through higher management?
Actually, I'm in the Volvo. I've worked with a lot of big data infrastructure stuff, so yeah, you can quote me on that.
Awesome, thank you. So we'll see. At the moment, I think it's also a challenge as data scientist. At least when you come from university, you can do pretty much whatever you get in your head in the morning. It's one of the biggest adjustments, but it's also, I see it as a challenge to not only adjust a bit to the environment you're thrown into, but also to try to change with little steps without people running away from you or getting annoyed. So, and it is a challenge to educate not data scientists on why you need certain tools, but in a manner that they can understand what the advantage is, and also in a manner that they know it won't cost that much to change. Unfortunately, the system decision costs anyway quite a lot. So. But it is a challenge, and yeah, I kind of like it. It's often frustrating as well, but I kind of like that challenge as well. Okay, next question. Do I still have time? Yeah, wow. Killian asks about the mileage dropping to 0. I sometimes work with count data and see a similar thing. It could be related to the number of bits that's used to represent the numbers causing a circular shift. Well, there are quite some words there that I don't understand. So I'm going to copy this question and give it to a technical expert. But thank you for the tip anyway. So thank you so much.
Yeah, so maybe
Then,
I can also add a little bit here. I've been working with the data
please.
as well for a bit. And basically, obviously there are certain possibilities like this, but in this case, in many examples, we are seeing it at different values. Because if we are talking about bit shift, there would be a particular value beyond which it just resets, right? And we are not always observing it at the same in the same situation. So I don't think that really explains it very well. There are a couple of different possible explanations, and one of the most kind of both surprising and annoying ones is that many of those things can just be caused by software resets. You upload a new version of the software, and this new version doesn't keep all the same memory, so you suddenly forget things like mileage and so on, which it's so annoying because it shouldn't really be very
logical
difficult to prevent.
So we might have a look at software changes then for that part. Okay, thank you for the tip. I'll take that into account. Thank you so much. Then Richard had another question. One of your speed issues and modeling issues stems from the fact that there are so many different fault codes, right? But there are not so many original features like temperature, right? Wouldn't it be possible to estimate which original features are the reason for the fault codes and then work with those original features instead of working with the fault codes? You also get a continuous space instead of a discrete input space, making everything data science related much easier. Yeah, I would love to have the parameter values, like for example, temperature and so forth. That said, we're quite restricted into what's being able to be sent from the TGW to our servers. And unfortunately, it's only be able to send through mostly summarized data, meaning the fault codes. So even though I would love to grab my hands on the parameter values, because indeed it would make life so much simpler, but unfortunately that's not with the current technology that's installed in the truck possible. There are some few parameters that are being sent through, but those are exceptions and those are quite critical for other operational stuff. But you're totally right again, Richard. So yeah.
But maybe it's not clear what I'm suggesting, because I'm not suggesting that you work directly with the original features. What I'm suggesting is slightly different. Changing the whole fleet from sending fault codes to sending the original features, that is going to be very difficult and very costly, and you would have to do a lot of changes. I totally agree. Yeah. So I'm not suggesting that. Instead, I'm suggesting, imagine you get a fault code. Yeah. So this fault code has been generated because of a certain thresholds have been activated, maybe even a combination of thresholds by the original features. So for example, this one fault code A comes because temperature is on a certain level, but you don't know how the other features maybe look like if you look at this fault code. The experts that you already have, they probably know what this fault code means. They know, they look at the fault code and they see, well, this fault code happens because the temperature was too high, above this, and let's say above 70 degrees. Or they look at the other fault code and they can say, well, this fault code happened because of this and this is beyond that and that. So what you do is then you consider your data point. Let's say instead of, you say that fault code is basically a data point in my original feature space where the temperature is at 70 degree, because I mean it does when it gets above, right? But you know that once it gets above, so it must have been 70 degrees, because then this is the moment you get the fault code. While the other data points, for example, what else do you have? Temperature, maybe pressure. You don't know anything about pressure regarding this fault code, because this fault code is not activated by pressure whatsoever. So you treat it as a missing value. So what you get, or you have a different fault code where it's not a missing value pressure, but maybe it's something like pressure must be between two values or whatever. Could be all kinds of stuff. So what you get is a messy data set. So you transfer your fault code into a messy instance of temperature and so on, or temperature and pressure. And some of the temperature and measure and temperature, those things, these original features, they are missing or they are vague, uncertain. And but at least you got sort of this new data set. Now there exist algorithms that are able to deal with this kind of data, like with missing values, uncertainty, and so on and so on. So you cannot use your out-of-the-box SPSS modeler model, of course, but you can use, and you are going to transcend to Python, right? So you are going to be able to work with this kind of messy data set. I think it will still be better than the fault code, though, because the fault code also does not have anything in this example about pressure. So you don't have this information about the fault code.
Sorry, Richard. It's very interesting question.
Sorry. But you got the idea, I think.
Thank you. I got the idea. It's something similar we're currently trying. So thank you for for reassuring that we did a great. We had a great idea.
To give the kind of conclusion and summary, but I just wanted to give you a very quick answer. In an optimistic world, yes, that would work perfectly. In reality, that would be a problem because first of all, those fault codes are very complex in many cases. It's not, unfortunately, as simple as temperature is above 70. Its temperature is above 70 and 20 other conditions that need to be fulfilled. And it's also the data set you would get would be extremely sparse. There is thousands of different fault codes, but they all come from tens of thousands of signals. So it's not like the underlying data is 20 signals that you could try to reconstruct. That is actually significantly more complex than that. But I think it's really interesting direction. If only we had slightly better fault codes. I think that's well.
Yeah, and a slightly better communication between the guys who are developing the software and our team. So that's also a challenge.
Okay, so
thank you so much for your attention and questions.
Olga, the floor is yours.
So thanks a lot for the great discussions and questions, and particularly for your insights, Jessica, into our real world problems. Was really interesting to follow the presentation, but also there are many interesting discussions as well. So we wanted to conclude this tutorial a bit with an outlook, also showing what we didn't show. Obviously, we did have quite some limited time, and we wanted on the one hand to go a bit into the detail, but also to give perspectives on different aspects. And the question is, where are we now, and where do we go from here? So what is there left to do? What are some of the open research questions or some directions that are quite promising to pursue? And if some of you have been following the hybrid direction, so it has been one of the magic keywords that has been used recently in a lot of different applications, and one of them is, of course, also the predictive maintenance. So what do we mean actually by this hybrid? And there are many different approaches to it, but also many different algorithms. So the idea is, on the one hand, that we are using deep learning models, so that since they have shown to be quite powerful, but then we are enriching those models, so either with physics, with some rules, some constraints, some prior information, some domain expert knowledge, or even with physics-based high fidelity models. And there are also different or different options on how to plug in and plug out the physics and combining it. So we can really go into many different aspects. So we can use deep learning for calibration of our physical models, which has shown to be performing quite powerfully, particularly for real-time parameter updates. We can substitute some parts of the physical models with surrogate deep learning models. We can enrich actually our observations with the observations from the physics or systems models, and then combine it in the deep learning models to improve our forecast. We can go in the direction of generative deep learning models, but still adding physics on it by some constraints or inductive bias. we can use also the deep learning models to cover some of the parts that our physical models are actually not covering, for example, by adding some discrepancy terms if we are not covering completely the physical models. So this is just providing some overview because we can also go directly into the deep learning models and integrating the physics-induced neural networks, for example, that enables us to approximate our models quite precisely. So that's one of the quite promising directions. And one of the reasons that is quite promising for predictive maintenance is that we saw that we are lacking a lot of data actually, and particularly for predicting the remaining useful life, it has been quite challenging without the labels and without the relevant data sets, and we are not going to collect all the relevant labels. So one of the possible directions to go is to enrich our models with the physical information, and that to enable us to go not just from early detection, but to go all the way to prognostics to enable us to predict the remaining useful life. But the other question that Jessica was also touching quite a lot was also how to support the domain experts. We do have quite a lot of models and quite a lot of information, but the question is how to prioritize, but also how to interpret the outputs of our models. And one of the next steps is not just how to interpret it, but also how to improve the operation based on what we have learned from the models. So how really to provide the information and learn from, for example, from good operators to transfer this knowledge to further operators, but also how to schedule our maintenance in a way that combines all the relevant information because it starts getting overwhelming. So even if we know when the system is going to fail, there may be still some uncertainty, but also we may need to combine it at a higher level, so not just a component level, but also at system level and also at fleet level. So this is also a relevant direction to pursue. And how can we use the information on the system condition proactively? So if we're predicting how the system is going to evolve and how the condition of the system is going to evolve, so if you're able to really to do that, so why are we not using it in the operation and actually going in from smart maintenance to smart operation? So that is also one of the promising directions. Well, a lot of you, or most of you, are probably machine learning experts, and this has been shown to be kind of the success factors of artificial intelligence, or the advancements of hardware, the emergence of big data, but also the advancements in machine and deep learning. And one of the limiting factors for us in predictive maintenance has been actually the emergence of big data. And what we are always trying to do is how to overcome these limitations. And these were the talks that you saw so far. So how do we deal with that, and how do we develop models and algorithms that are capable of dealing with that? But one of the directions is also to start sharing the data set and the knowledge across companies' borders. Sorry? Okay, if there is a question, I did not get it. So this is one quote actually that is from 2016, that actually data sets and not algorithm might be the key limiting factor to the development of human-level artificial intelligence. And for us, it is actually one of the most limiting factors that we don't have these data sets, this benchmark that has served, for example, the computer vision so much. And whenever I'm given the opportunity, I'm trying to promote that actually sharing the data sets across companies' borders could be the way to go. And it's not that we have that the companies have to provide all the information. It's also possible to share algorithm and not the data set, so that the data sets still remain private. But this would enable really to foster the developments and also to share the experience, because in a lot of cases the companies are not directly competing, and that could provide some opportunity to develop this really further. So what ultimately we are trying to achieve is to have the algorithm that are actually generalizable, that are scalable, that are self-adaptable, interpretable, and robust. And these are high goals, but you saw that some with the 3 talks that you saw today, how we're actually on the way to make it more interpretable, to make it more scalable, more generalizable. And of course, we would like to have algorithms that are really robust and that are adapting to their operating conditions. So that was a bit fast. I'm 3 minutes over time, but I hope you got some insights. You got some of the ideas to pursue further. Thank you very much for Slawomir and Joao for organizing this and for the opportunity to discuss it with you. And if there are any further questions, please address them to the speakers that are most related to. Thanks a lot.
Thank you very much for the summary, Olga. Thank you everybody for joining this tutorial. I thought it was both interesting and helpful, that you have learned something and you had a good time. And if